I congratulate the entire team for their dedication to academic excellence and skill development in cybersecurity. We live in a time when the digital world is intricately woven into the fabric of our daily lives. From smartphones and connected vehicles to digital payments and telemedicine, technology drives convenience, productivity, and global connection. However, as we adopt these benefits, we must face the growing threats that accompany them: data breaches, ransomware attacks, misinformation, campaigns, and other cyber attacks. In this context, the theme of this workshop, Secure Cloud Computing, Artificial Intelligence, and Distributed Systems, is not just timely but essential. It reflects a recognition of the complex, multidisciplinary nature of modern cybersecurity challenges. Cloud computing has enabled tremendous scalability, cost effectiveness, and flexibility. And with this power comes significant responsibility. A single vulnerability in a cloud deployment can expose entire ecosystems to risk. Similarly, distributed systems must be designed to withstand faults, maintain data consistency, and protect against malicious interference. There is a growing need for secure design principles, compliance with regulatory frameworks, and practical awareness of system behavior under attack scenarios. Artificial intelligence, another core pillar of this workshop, is revolutionizing every sector from education and agriculture to healthcare and defense. In cybersecurity, AI is a powerful ally. It can detect anomalies, automate threat detection, identify malware patterns, and improve incident response. However, AI also introduces new challenges. We now deal with adversarial attacks on machine learning models, deepfake generation, model extraction, and privacy breaches. Therefore, the use of AI in security must be guided by ethical standards, accountability, and robust design principles. I am particularly pleased to see that the sessions in this workshop are not limited to theoretical discourse. They include hands-on tools and technologies such as Wireshark for packet analysis, MongoDB vCore for cloud data handling, and even explorations into federated learning and homomorphic encryption. These are cutting-edge tools and techniques, and I applaud the organizers for integrating depth and practicality into the curriculum. Another aspect that stands out in this program is its inclusivity and relevance to diverse participants, from undergraduate and postgraduate students to faculty members and industry professionals. This workshop offers something for everyone. It is heartening to see such platforms bringing together young minds, experienced researchers, and practitioners to engage in dialogue, share knowledge, and build networks. The hybrid mode also ensures greater accessibility, enabling participants from India and beyond to benefit from these sessions. Cybersecurity today is not just a technical issue, it is a national priority. It intersects with defense, finance, healthcare, education, and governance, etc. According to a report by the think tank Data Security Council of India, DSCI, India detected an average of 761 cyber attack attempts per minute during last year 2024, with the healthcare industry being the top target sector, followed by hospitality and banking. According to the Indian Ministry of Electronics and IT, cyber attacks on Indian government entities increased by 138% between 2019 and 2023, rising from 85,797 incidents in 2019 to 204,844 in 2023. India emerged as the second most targeted nation in terms of cyber attacks in the world, as 95 Indian entities came under data theft attacks in 2024. Cyber intelligence from CloudSec said in a report. Bharat Sanchar Nigam Limited (BSNL) suffered a major data breach, exposing sensitive information of millions of users, including IMSI numbers and SIM card details. The attack, attributed to a hacker named Kyber Phantom, involved the theft of over 278 gigabytes of data, which was offered for sale on the dark web. The Tamil Nadu Police's facial recognition portal, a software used by the state police to track criminals and missing persons using facial recognition, was compromised in 2024. The data samples were made available for sale on the dark web, and an analysis of the leaked samples indicates that 1.2 million lines of data, including names of police officers, phone numbers, and FIR details, have been accessed illegally. Recently, Resecurity, an American cybersecurity company, claimed that personally identifiable information of 815 million Indian citizens, including Aadhaar numbers and passport details, were being sold on the dark web. Threat actors were willing to sell the data for $80,000. It further said that the data on sale was found to be valid. The threat actors selling the data claimed it was sourced from the Indian Council of Medical Research, which has been subjected to numerous cyber attack attempts, with 6,000 incidents being reported last year alone. These incidents highlight the urgent need for a deeper understanding of cybersecurity across all avenues. These events remind us that cyber threats are not something that might happen in the future. They are already happening now and affecting millions of people. As our dependence on digital systems grows, so does our vulnerability to sophisticated cyber attacks. These events emphasize the importance of building secure systems, raising cybersecurity awareness, and developing skilled professionals who can anticipate and mitigate such risks. Spending time and effort on learning and researching cybersecurity is not just important for technology. It is also necessary to keep our country safe and strong. I would also like to reflect on the importance of faculty development programs such as this. As educators, it is our responsibility to constantly update ourselves with the latest tools, techniques, and theoretical advancements. These programs act as catalysts for curriculum revision, interdisciplinary collaboration, and applied research. They help ensure that what we teach in classrooms is aligned with what is practiced in industry and demanded by society. To the participants of this workshop, I would say make the most of this opportunity, attend sessions actively, engage with speakers, ask questions, and share your experiences. In addition, consider how you can apply what you learn here in your teaching, research, or while writing projects. The topics covered over the next 5 days are not just academic, they represent the backbone of secure digital transformation. Whatever it is, a privacy preserving AI, secure cloud architecture, lightweight cryptographic schemes for IoT, Internet of Things, or regulatory compliance for distributed systems. Each session introduces you to an important real world issue. In conclusion, I once again thank the organizers for conducting and putting together such a meaningful academic event. I praise their effort in promoting excellence in cybersecurity research and education. I wish all participants enriching experience over the course of this workshop. Let us work together to build a digital ecosystem that is not only efficient but also safe, ethical, and resilient. Thank you, and Once again, I wish SCADS 225 a grand success. Thank you all.
Thank you, sir, for your insightful and thought-provoking address. I am honored to invite on stage Dr. Jalaja MJ, Adjunct Professor, IIIT Kottayam, to deliver the felicitation address.
Respected Registrar Sir, respected Chief Guest of the Day, dear faculty, colleagues, and other delegates from various institutions, good morning and namaste. I am extremely proud and happy to attend this event. In fact, this is the second FDP in our organization because last week also we had last week I had attended one FDP jointly organized by IIIT Kottayam and NIT Kurukshetra. It was in online mode. And that Shani was the convener. And 3 of our faculty members had taken classes also, excellent classes, Guravaya, Venkadeshwar, and Shajilin sir, all of them. And I feel proud that we have such excellent young faculty members with very good knowledge and very good capacity to say deliver things. So, of course, it's a matter of pride for all of us. And from our chief guest, we have heard what exactly is the significance of FDP and also what exactly is the relevance of this particular topic. So I'm not going into such things. What I want to say, tell you is just quote the words of Mahatma Gandhi. Whenever I used to say address the delegates of any FDP, I used to quote this one. That is, we need to live as if we are going to die tomorrow. But we need to learn as if we are going to live forever. So all of us, whether faculty members, research scholars, students, people from industry, whatever it may be, we need to learn because technology is changing every second. So we need to learn, we say new technology, update every second. So I hope this FDP will provide you such an opportunity to learn more, to interact more, to collaborate with others, etc., etc. So please feel free to make utilization of this and interact with our faculty members and build new collaborative activities with our institute. Thank you for inviting me and wish all the best for the successful conduct of this FDP. Thank you so much.
Thank you, ma'am, for the insightful words. Next, I would like to invite Dr. Panchami V, Head of the Department, CSE Cybersecurity, to deliver felicitation address.
Good morning, all. Respected Registrar Sir, Jalja Madam, Chief Guest, Dr. Anand Sir, faculty, technical staff, research scholars, participants who are present here, and they have joined, the participants who are joined virtually. It's very pleasure to say that, and I want to congratulate Dr. Silambarasan and Dr. Jobin for conducting this 1 week FTP come workshop on secure cloud, AI, and embedded distributed systems. This workshop is technically sponsored by ACM Student Chapter IIIT Kottayam. As Registrar Sir told, this workshop has a special significance for our cybersecurity department, as this is the start of the beginning of a series of focused initiatives. Upon the next 3 months, our cybersecurity department is organizing various workshops, boot camps, certificate programs, training programs, and this workshop is the one or is the first in that lineup. Furthermore, this workshop particularly has a speciality because this is the first event conducted by the newly formed SCADS lab, and it's led by Dr. Silambarasan, and congratulations for that. SCADS lab focus on interdisciplinary research and innovation particularly having a focus on secure cloud, AI, and distributed systems. And I take this opportunity to all of you, those who are particularly interested, please connect, collaborate with Dr. Silambarasan and his team on behalf of SCADS Lab. Regarding the technical perspective of this workshop, and this workshop, you can see that it covers a various domains in cybersecurity, especially starting from the attack perspectives of cloud, impacts of AI, blockchain, and various attack perspective and defensive mechanisms in terms of distributed systems. I strongly believe that the participants who joined with us will get an insightful knowledge so that they can apply in teaching, learning, as well as their research pursuits. With these words, I wish all the participants and the resource persons and fruitful and insightful session ahead. Thank you all.
Thank you, ma'am, for your encouraging words. On behalf of everyone present here today, I would like to invite Dr. Jobin Jose, Assistant Professor IIIT Kottayam, to deliver the vote of thanks.
Respected dignitaries on and off the dais, dear faculty members, research scholars, teaching and non-teaching staff, and my dear participants. Good morning, one and all present over here. So it's my honor and privilege to deliver the vote of thanks for this associated with this 1 week FTP on distributed cloud and AI and digital systems. So on behalf of everyone present over here, first and foremost, I would like to extend my sincere thanks to Professor Prasad Krishna, our director, for his constant support and motivation. Thank you, sir, in his absence here. I would like to thank our esteemed chief guest, Dr. Y. Srinivas Rao, Assistant Professor, NIT Warangal, for his inspiring keynote address. Sir, your insights have truly set the tone for the week ahead. Thank you, sir.
Thank you, sir. Thank you.
I would also like to express my sincere gratitude to our researcher, Professor Dr. M. Radhakrishnan, sir, for inaugurating the SPP and sharing the words and words of encouragement. Your continued support and guidance are invaluable to all of us in our all endeavors. Thank you, sir. I would also like to express my heartfelt gratitude to our HOD, CSE Cybersecurity, Dr. Panchami V, for the kind words during the felicitation address and for her leadership in making this event possible. Thank you, ma'am. I would also like to express my sincere thanks to Dr. Jalaja ma'am for accepting our invitation and sharing the dais and delivering the felicitation. Thank you, ma'am. A warm thanks to Dr. Silambarasan, the coordinator of the FTP, for the welcome address and for being the driving force behind this workshop. Thank you, sir. A word of gratitude to our research scholar, Ms. Chelsea, for her inaugural prayer song. To all of faculty, staff, research scholars, both participants, both online and offline, thank you for your enthusiastic presence and support. Your participation is what gives the meaning to this initiative. Thank you all. Last but not the least, I would like to thank the organizing team, the technical and non-technical staff who work tirelessly behind the scenes to make this particular event smooth and successful one. Thank you all. Let's begin the journey with learning and exchange of knowledge and ideas. Thank you once again.
Thank you, sir. Now, I request everyone to raise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता। पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा। विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा। तव जनगण मन अधिनायक जय हे भारत भाग्य विधाता। पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा। विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा। तव शुभ नामे जागे तव शुभ आशीष मांगे। गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।
I would like to take this opportunity to extend my gratitude to everyone present here. Thank you for gracing this inaugural event with your presence. Tea and snacks are served outside the lab. Kindly refresh yourself.
Thank you.
Yes. Topic. First slide. I am starting with clear, sir. Otherwise, I have not finished.
Well, next, we welcome Dr. Renu Mary Daniel for the first session. Renu ma'am is Assistant Professor at IIIT Kottayam, specializing cryptography, digital forensics, and information security. She holds a PhD in computer science and engineering from Karunya University, with her research focused on the design and cryptanalysis of public key crypto systems based on elliptic and conic curves. She is a recipient of the prestigious Vishwesvaraya PhD Fellowship from MeitY Government of India. Dr. Renu has conducted training sessions for central and state police forces under the Ministry of Home Affairs and serves as a reviewer for reputed journals, including Access and Nature's Scientific Reports. Her research contributions include several SCI and Scopus indexed publications in the field of secure key agreement, sign encryption, and identity-based encryption. We welcome you, ma'am, for the session.
Good morning, everyone. I hope I am audible. Good morning. Yes. Okay, so my session today will be about, initially I will be giving an introduction to the TCP handshake, three-way handshake, and then we will move on to TLS handshake, and how the encrypted tunnel is prepared in TLS handshake. What are the encryption mechanisms or cryptographic mechanisms that are involved in creating that TLS tunnel, encrypted communication channel between client and server. So before we move on to that, first I want you to open Wireshark and we will do a small capture of an HTTP traffic. and we will analyze it, and then we will move on to HTTPS traffic, which we will encounter mostly. HTTP is now only for experimentation purposes, so we will usually see only HTTPS traffic. So first we will see HTTP traffic and how to analyze it, and then its vulnerabilities, and then we will move on to HTTPS traffic. Right. So you can open Wireshark. It will be already installed. So since I am, are you all able to see the screen? No? Uh, okay, now you are able to see the screen? Excuse me? Yes. You have opened Wireshark. You are able to see this. Yes. Okay. ഇവിടെ അല്ലേ? Okay. Open now. Choose Ethernet. Choose Ethernet. Ethernet. First, we will be connected by Ethernet. Okay, when I ask you to choose, you have to choose Ethernet, not to Ethernet. No, no, no. Here, here. Can you start capturing? Can you visit some sites, Google, somewhere? Take some, open some browser. Okay, now search something. Search something. Okay, now start capturing. I just want to see if it's getting captured. Yeah, okay, okay. Okay. So I hope you are able to see the screen. Okay, now we are going to capture some packets, search for something and capture some packets. So you have to select whatever you are connected to, whatever interface you are connected to. Since I am connected to Wi-Fi, I have chosen it over here. Beneath the display capture filter, you can see Wi-Fi, Ethernet 2, Ethernet 3. I am connected to Wi-Fi, so I am choosing that. You have, if you are connected via LAN, you have to choose Ethernet. Okay. I hope you have chosen, and now you have to click on this sharpen on top, start capturing packets. I hope you can see towards the top, left hand side top, you can see a shark fin. You can click on it and it will start capturing packets. So before that, make sure that you have opened some browser and you are ready to browse. Done till here? I'm starting my capture. And what I'm going to search for is, in Google, I will search for HTTP login page. I'll search for HTTP login page. And the first search result you can see is that home of Accunetrics art. So you can click on that. And there you will see a vulnerable page that's only for testing purposes. There you can enter a username and password and click on login. Any username and password. I'm giving Nano and IIITK and I'm clicking on login. Okay. So after this, you can go back to your Wireshark capture and stop capturing. Okay, this much is done. I hope this much is done. You've all captured the packets?
Yes.
You should be able to see something like this. So in my window, I am able to see the packet number, time of capture, delta. I'm not sure if everyone is able to see all these columns. Actually, you can add those columns as per your desire. Since we have a separate session on Wireshark and how to use Wireshark, I'm not going into the details of it. So I hope you can see at least the ones that I'm telling you, the columns that I'm telling you now. The number, packet number, you are able to see number, right? Number, then time of capture. Leave delta. That's delta is the time difference between the previous capture and packet and this packet. Time difference, delta time. Then source IP, destination IP, protocol, source port, destination port. Then that's enough. At least that much should be there. And info will always be there. Can you see at least that much, everyone? If you are not able to see any of these windows, you can go to Edit, Preferences, Edit, Preferences, then Columns. And from here, you can add the columns, add whatever columns you want, or delete the columns that you don't want. For example, say if I'm adding one column, suppose the protocol column was not there. So I'm going to delete this, okay. Delete this. I've deleted the protocol column. So if I want to add it once again, I can click on the plus sign. And here I can specify the column name, protocol. Then here, if you click on it, you can see different options. There, from there itself, you can choose protocol. And give apply, okay. Like that, you can add and remove columns. I hope this much is clear. Yes? Okay. Now we are interested to see the HTTP traffic. So we want to view because others are all encrypted. So because I have now used, do you know what are the different commonly used HTTP request methods? HTTP request methods. Get method is there, which we use to pull some resource from the server. Then post is there. So if you are submitting some data, some resource, user data to the server, we will be using the HTTP request called post. Then if you want to update some resource, the HTTP request that will be used is update. Okay, if you are updating parts of it, then we'll use patch. And for deleting some user resource, user data, we use delete method. So these are the most commonly used methods. So when the user is submitting some user data, which HTTP method will be used? When the user is submitting some user data to the server, which HTTP method will be used? Post will be used, post. Okay, when we are getting some pages from pulling some pages from the server, get will be used. So now I want to see the username and password which I submitted in that HTTP page that we visited. Okay, so to do that, we are going to filter only the related to HTTP traffic. So here you can see a display filter on top. This is the display filter. So here if I key in HTTP and press enter, only the HTTP traffic will be listed here. Okay. So you can see that only the HTTP traffic is being listed here. Since we have only few packets here, from here itself you can see the post request. See, post request. Otherwise, if we had lots of packets there, you can even search for a specific HTTP request like this: HTTP dot request dot method equal to post, and press enter. Only that particular post request will be seen here. Okay, this much is clear, everyone. Post will be seen here. Now, if you come to this section, can you see these two windows here? This window over here and this one in hex details window over here. Now here you can see hypertext. You can see the different layers. Layer 2, Ethernet, then layer 3, network, then transport, then application layer of the TCP IP stack. You can see all of them here. And you can see that the application data is in some HTML form. So if you click on that, you can see the username and password that I had submitted. Okay, so this much is clear. So if somebody is capturing your packet and you are using HTTP, all your data can be retrieved. Not only this, they can identify all the pages that you have visited. For example, if I do over here, right click, follow HTTP stream, you will be able to see all the pages that the user has visited pertaining to this particular website. Everything that the user has visited. And here, even here, if I search for something that, for example, since I know the password, you can see that there you can see the username and password here also. And even from file, that also I'll show you. File. From here also you can export objects, HTTP objects in this capture. All these HTML, even PNG, any images, all those things will be listed over here. And you can save it all to some folder later for analysis. So this is how you can recreate what the user had done previously for an HTTP traffic. Okay. Now what I want you to look for is, are you able to see this, the SYN-SYNAC app? You do right click on that HTTP post request and do follow HTTP stream. Had you done that? Everyone, did you do that? Otherwise, you will not be able to see the SYN-SYNAC app. Right click on that HTTP traffic, right click, follow TCP stream. If you can give either follow TCP stream or follow HTTP stream. This will be listed in this order. The communication that my device, this is my device's IP. My device is done with that server. The entire communication in that order will be listed here. If you follow TCP stream for that packet. Are you all with me? Can you see this conversation starting from Cincinnati? No? Please respond, okay? Everyone, please respond. Are you able to see or not? No. Okay. Were you able to figure out the post request? Did you find the post request, everyone? Got it now? Then it will be very easy. So this is getting listed for everyone, right? Everyone got this? Now right click on this particular packet, right click, follow. You can do follow TCP stream. Follow TCP stream. Right click on that particular packet, follow TCP stream. You can close this window. Now you will be able to see this entire conversation between my system and that vulnerable server, that website, that server. You can see the entire conversation starting from this is the first packet. I hope you understood this much. Are you able to see this? Starting from Cincinnati. Please say yes or no. Yes? Boys over there? Yes. Excuse, what is your name? Jumna is able to see? No. HTTP. ഇതാണ് we follow TCP stream. In the first packet നോക്കാം. കണ്ടോ? Cincinnati, okay. Right. So first, this is called as the TCP handshake. So HTTP 1.1, 1.2, all of them use TCP in the transport layer. Okay, HTTP 1.3 uses quick and thereby it uses UDP. So here you can see that first communication in a normal TCP communication, the first packet, this is from, can you say which one is the client and which one is the server and why? Looking at the ports, port numbers, which one is the ephemeral port here? Large number. That's the source port. This one, 60217. So it is initiated by the client, which is me. And so my IP address is 172.16.208.203. So client is initiating this first synchronized. Syn is synchronized. Okay, first syn packet that is from the client. Okay, what is getting synchronized here? What is getting synchronized? The sequence, the client is actually sharing. You know that TCP is a connection-oriented protocol. So the client is now sharing the initial sequence number of the client. Okay, in this packet, so if you come over here, click on that first SYN packet, click on the SYN packet, TCP. You can see source port, destination port, and you can also see something called as everything that is in square bracket is assigned by Wireshark. Okay, for our ease of understanding. So this is the stream packet index 6. Okay, so this stream packet index you can see over here also, TCP stream equals 6. So that denotes a unique four tuple consisting of a source, consisting of these two IP addresses and these two port numbers. It is a four tuple. Okay, four things are involved in that. This IP, this source, this port and this port. Both way. It's not ordered. It's not an ordered tuple. Okay. It can be from client to server or from server to client. Both way communication included. So all those packets are listed here. So all of them are included in TCP stream equal to 6. It's a four-way tuple. Like this, for every communication between two hosts, There is a TCP, unique TCP stream number. Okay. Now, if you come over here, you can see sequence number row. Are you able to see sequence number row? In my case, it is 30319044241. Like that, you will be able to see in your system the sequence. That is what is getting synchronized here. Client is sending a synchronization request to the server, providing its initial sequence number. So you can see that my client's initial sequence number is a very large number ending with 4241. 4241, just remember that, 4241. And what is the acknowledgement number? Can you see the acknowledgement number row? Acknowledgement number row is 0. Why? Because I haven't received anything from the server. So my acknowledgement number is 0. I haven't received anything yet from the server. Now, click on the next packet. So remember, in my case, the sequence number is 241. Initial sequence number of the client is 241. So I am clicking on the next one, which is SYNAC. SYNAC, this is from whom to whom? This is from the, look at the source address. This is from the server to the client. Server to the client. The server is doing what? Server is again sending a synchronization request to the client. That means this packet will contain the server's initial sequence number. Also, it will contain an acknowledgement number for the packet that is received from the server, client. Is that clear? So if you remember, my client initial sequence number was 4241. You can see the acknowledgement number row ends with 4242. Can you see that? You can check in your systems. In my case, it was 4241 for this packet, sequence number of the client. So the acknowledgement number that the server sends back is 4241 plus 1, 4242. And also you can find the sequence number of the server in row, which is 7578. Can you see? Initial sequence number of the server. So completely different number, 7578. Okay, got it? Next packet is from whom to whom? Next one. Only that acknowledgement. That will be next from the client side. ACK will be from the client side. Okay. Now, if you look at the ACK, so this 747, what will be the client's acknowledgement number? What do you think will be the client's acknowledgement number in that ACK? 7578 plus 1. Okay, server sequence number plus 1. That's what it is hacking. Okay, server's sequence number plus 1. So we should be seeing 7579. 7579 in the acknowledgement. So you can see it over here, 7579. And the sequence number of the client is the initial sequence number, whatever it was, plus 1. That is 4241 plus 1, 4242. This is what is happening. The synchronization is happening there initially. This is called as TCP three-way handshake. This will happen first. Okay. Then, since this traffic is unencrypted, we are able to see everything. All the rest of the application data is unencrypted. Okay. Now I had shared a PCAP file with all of you. I hope it's already shared. You can open that packet. Okay. So now what you need to do is, if you have that file, open that file. Otherwise, just do one small thing with me. You can just close that page, HTTP page, which we just visited. No, close that page. Close that page. You all have your college LMS login IDs. No, college LMS login IDs. All of you have, or some Gmail, whatever. So what I want you to do is, now we are closing all the HTTP sites. and then again do Wireshark capture. Click on that shark fin once again. Click on that. Okay, now I'm going to visit our LMS and I'm going to log into that. Okay. Okay, I've closed it now. So you know that now I have also submitted some username and password in a form, right? So actually I have done an HTTP request method equal to post is done there. But if we once again check now, HTTP dot request method equal to post, let's see if something gets displayed. You can see that it is empty, but actually I've submitted some data. It's not visible. Why do you think? Because it's all encrypted. The traffic with my server, LMS server over here is encrypted. It's via TLS. Okay, so it's encrypted. You won't be able to see anything in clear here. So we are going to see how that encrypted tunnel is formed. So for that, you can open that TLS 1.2 explanation. Here. Can you see? Can you see this first packet, first three packets there also if you look at it? What are the first three packets? Sin, Synac, Act. Did you see that? Sin, Synac, Act. Here also I have some data, but you can see that after that we have a client hello, then we have a server hello, then we have client key exchange, change cipherspec. All of these application data, wherever you see this application data, some forms we are visiting, user is visiting some form, submitting some data, but you will not be able to see what HTTP method is being used, whether data is being submitted. Nothing you will be able to see, because if you click on that application data, any of the packets with application data, if you click on that, you can see, did you see this? Encrypted application data. Can you see that? Encrypted application data. Click on any packet containing application data. Click on, after the TCP layer, you will have transport layer security. Within that, you will have encrypted application data. Nothing will be seen in clear. Are you all with me? Did you all do till here? No. Did you open this packet? Can you look at any of the info where application data is seen? Application data. Any of the packets where you can see application data. No. The PCAP file mail. PCAP file. Mail. Others got it?
Got the file, no?
Boys? PCAP file. കിട്ടിയാ നിങ്ങൾക്ക് കിട്ടിയാണോ? It's okay, just log in and see. Okay. Those who have joined online, can you confirm whether you have got this file? Anyone? Anyone, can you respond?
Ma'am, I'm
Yes,
following it, but I'm not able to proceed because YXX is not working for me. So I'm trying to fix it at my end.
Sir, I'm not able to understand what you are saying. Can you put it in the chat?
Yeah,
No. Sir, once again, can you confirm whether you have this PCAP file? Whether you are able to see this conversation? Okay, thank you. Yes, sir. Sir, like this, you can fetch it and see. Okay, I hope it's now open, everyone. For everyone, it's visible. Click on this application data. Any packet containing application data, you will be able to see in transport layer security that it is encrypted application data. So where does this TLS come in the TCP/IP protocol stack? It will come in between the application layer and the transport layer. In between the application layer and the transport layer. So something like this. Okay. At the application layer, we have all those protocols. In between the transport layer and the application layer, we have the SSL TLS layer. So it will encrypt all the application layer data. So the payload will be encrypted. We won't be able to see even the methods that are used. Okay. Now, before I go into the details of how this encrypted tunnel is formed, we will quickly go through the basics of some of the cryptographic techniques that are used to form this tunnel. Okay. So this slide, I hope, is clear with the SYNAC app, right? After that, okay. So few of the cryptographic techniques that are used to form the tunnel. One is symmetric key cryptography. So if you are in BTech, no, UG, you have learned the course cryptography? No. Boys over there, you have learned. Okay, so I'm not going to the details of the algorithm, just the concept I will tell you. So in symmetric key cryptography, so there will be, you know that there will be two peers, a client and a server usually, and these peers will be sharing a common key which will be used for encryption. Okay, a common key will be used for encryption. So you can see that we use the mechanism of encryption, make the data unintelligible. Only the intended recipient should be able to see the data. So I'm encrypting it and sending it to the other side. Only the intended recipient should be able to read the data. And the mechanism, cryptographic mechanism that we use here is symmetric cryptography, means that both the client and server share the same cryptographic key, share the same key. That means I should have some mechanism whereby this Alice over here, let's say it's a client, and the Bob, which is a server, say bank, both of them has the same set of keys. So these keys are all numbers. And we'll be using, in simple terms, some function so that we'll take a plain text message, apply this number with the function, and create something that no one can read. Okay? So only Bob can read it. So it's like sending it with this lock, padlock. Plain text will be sent with this padlock. What is the specialty of this padlock? It can only be unlocked with the same key, right? It can only be unlocked with the same key. So this is symmetric key cryptography, and so he'll be able to get back the plain text. The Eve is another term that we use for an attacker who is always listening to the channel. Eve is always listening to the channel. Eve will only be able to see the encrypted message or a ciphertext. So with the ciphertext, Eve will not be able to derive anything because Eve doesn't have the key. Okay. So the one problem with symmetric key cryptography is we need some way to securely share this key between the sender and the recipient. Okay, either they have to meet up or they should have some another encrypted tunnel whereby they can share this key to the server. Server and client can share this key securely. Let's say they meet up and they share this key. It's not possible for anyone else to get the key. In that case, this is completely secure. And symmetric key cryptography is used for bulk data encryption because it is more efficient than asymmetric key cryptography, which we'll see shortly. So please remember that symmetric key cryptography will be used for bulk data encryption because it's much more efficient. And some of the algorithms that are used are AES, CHA-20, triple S, like that. Blowfish, we have several algorithms. AES will be the most used choice, and CHA-20. Okay. Now, another disadvantage of symmetric key cryptography is that you can see that if symmetric key cryptography is used for some banking application, then what does that mean?
Hello.
Remember, grandmothers used to carry keychains like this for every door with her. Like that, bank will have to share a unique key with every peer. With every peer, a unique key has to be shared. So this issue is persistent in symmetric key cryptography. So here, two things are ensured. One is confidentiality. Confidentiality means that only the sender and the recipient will be able to see the data. And authentication. If I send some, if I receive some encrypted data and Alice is able to decrypt it with a key, then that means that the data is sent by Bob only. Why? Because Bob only has the key. So if I receive that data and I am able to decrypt it correctly with the key, then that means Bob has sent it. No one else has the key. So the authentication means that we are verifying the authenticity of the sender of the message. Okay, next is public key cryptography. So here you can see another kind of lock, a Chinese lock and a key. Okay, so there are two pairs of two keys. So if you look at this symmetric key cryptography, one example for this is XOR. XOR gate, you all know XOR gate, right? XOR. So here same key will be used. For example, if 1011 is my key, here Bob will also have 1011. If my plain text is say 1100, what will be the ciphertext? What will be the ciphertext? 1110. Am I right? We'll be sending that to Bob. Bob will apply the same key on the ciphertext. So we will have 0111. Apply this key 1011. What will happen? We will get 0011, which is our plain text. So this is how symmetric key cryptography works. Now, if we move on to asymmetric key cryptography, so remember everything that I show here are numbers and we use some functions. It's not lock and key. Okay, so now these two keys, there are two different keys. And these two keys will be mathematical inverses of each other. Okay, the effect of one key, the other key will cancel it off. That's how it works. So there is something called as a public key and there is a private key. Bob will keep his private key safe. He will not share it with anyone. But this public key, Bob will share with everyone. So he will send this public key to Alice. He will also get it. Now Alice will encrypt some message, send it to Bob. Alice is sure that only the person who is in possession of the corresponding public key will be able to decrypt it. Okay, that she is certain. Do you understand? Only the person who is in possession of the corresponding key can decrypt it. Okay, so these two keys are mathematical inverses of each other. I've shown the decryption, encryption, and decryption functions there. You can see for encryption we use the public key, and for decryption we use the private key. That is clear, everyone? Okay. So here we only have confidentiality. We don't have authenticity. Why? Why do you think we don't have authenticity? See, Bob is getting some message from Alice. Does he know that this message is from Alice? This message can be from Eve, it can be from someone else. Bob doesn't know whether who this message is from. Do you understand? So his confidentiality is ensured here. Okay, so this is how banking problem we have a solution. Bank will share the same public key to everyone. Everyone will encrypt with the same key and send it to the bank. Okay, bank doesn't have to maintain a key chain for that, unlike symmetric cryptography. Do you understand? Same public key can be shared with everyone. I hope it is clear. And he can decrypt, bank can decrypt it with the same private key, any of these messages. Okay. Another thing is digital signature that's associated with public key cryptography. So what happens is that now Alice wants to send some message to everyone. So if you have your degree certificates, is there anything confidential in your degree certificate? Degree certificate, you have marks there. Is there anything confidential there? You want to show it to everyone, right? You want to show it to everyone. What is the thing that you want to make sure? See, this is authentic. This is from mine. This is from IIIT Kottayam. That's what you want everyone to understand, right? So we want authentication of the certificate. We want authentication. So how is authentication ensured? Somebody is signing there. Do you notice the dean, the registrar, everyone will sign there. HODs will sign. So that sign ensures that this certificate is in fact from this organization, right? So if Alice wants everyone to know that this message is from her, what she will do is she will sign the message. Okay, that is, she will encrypt the plain text with her private key. She will encrypt the plain text with her private key and she will send the message. Okay, we call it as the signature. She will send the signature. Now what will happen? The signature attacker will also get. Now how can the attacker decrypt it to get back the original message? Using what is the inverse of this private key? The public key, right? The public key will cancel the effect of private key will cancel the effect of public key. So everyone has key. We will apply the public key and they will be able to verify the message. Do you understand? So this is called as signature. Here our goal is not confidentiality. We want everyone to see it and understand it. But we want everyone to believe that it is from us. Okay. So here the goal is sender authentication. This is called as digital signature. I hope that is clear. Digital signature, sender authentication. All right. So why we use public key cryptography is, see, symmetric key cryptography has one main problem. What is that? I am never going to meet up with a server and share a key. Right? I can't share a key by meeting with them. We are not meeting with anyone. So the one way to securely share an AES key or some symmetric key with another server is through this public key cryptography. Okay, we use public key cryptography only for what? Sharing keys, sharing symmetric keys. Bulk encryption is always done using what? Symmetric key crypto. Are you able to understand? Bulk encryption always done with symmetric key crypto. So there are two ways to do it. One is using key transport. Another one is using key agreement. Okay, key transport is done like this. Let's see. So key transport using public key crypto. What Bob will do here? Suppose Bob is a server. Okay, please listen here. This is the core. Bob is a server. Bob has a public-private key pair. Okay, Bob will send his public key to Alice. Now Alice will choose a random symmetric key for bulk data encryption between both of them. Okay, and Alice will now encrypt this key with what? Alice will encrypt this key with, can you tell me? With the public key of Bob. Now who will be able to decrypt it? Only who will be able to decrypt it? Only the bank. Yes. Okay. Only the bank will be able to decrypt it. So it will be encrypted, sent, and now the bank will be also able to get the symmetric key. Now the rest of the communication will happen with the symmetric AES key. This is called as key transport. This is one mechanism that is used in TLS version 1.2. Okay, with RSA. RSA is one of the public key crypto systems. With RSA public key, server's public key, symmetric key will be encrypted, sent to the server by the client. Got it? This is called as key transport. In the most recent TLS version 1.3, we don't use this anymore. You know why? Suppose the server's private key is compromised. What will happen? Server's private key is compromised. What do you think will happen? See, Alice is sending the session key, symmetric key, encrypted with the public key, and sending this main information to the bank. What will happen if anyone has Bob's private key? They will be able to decrypt it and get the key, AES key. Do you understand? So this is not used in TLS version 1.3 anymore. So instead, what is used is Diffie-Hellman key exchange. Diffie, I know it's too much to process. Please hang in with me. So we have Alice and Bob. What we do now is nobody will share any secret information over the wire. Both of them has a pair of public-private keys. Both has a pair of public-private keys. They will only share their public keys. And so Bob will send his public key to Alice will mix private key to that to create a symmetric key. Okay, Alice will send her public key to Bob. Bob will mix his private key to make a symmetric key. Both will be equal. So now there is no issue. No man-in-the-middle attack can happen. Okay. So now you can see there is a private key. This involves something called as primitive root and prime number. We don't have the time for that. So there'll be something called a prime number, and there'll be field is a P star. And alpha is a primitive root. If you raise alpha to different powers, you will always get a number between 1 and P minus 1. So what we do is modulo P operation. I won't go into the details of that. Just understand, just think that we are playing caroms. I am playing caroms. I have a caroms board. I show you the starting point and I ask you to turn around. Okay, I show you the starting point where my striker is. And I ask you to turn to the other side. Now I am striking it randomly for some number of times. That number of times is my private key. Now I show you the endpoint. I show you the endpoint. Can you tell me how many times? It's not possible because it will always be inside the board. Okay, like that. Key, public key. 1 and P minus 1. So there is no one can know what A is given alpha power A. This is how it works. So you send alpha to the power A to will be sent to Bob. Bob will send alpha to the power B to Alice. Now Alice will do this alpha to the power B, the whole to the power A. So what is alpha to the basic math? Alpha to the power B, the whole to the power A. 8th standard math. Alpha to the power AB, no? Right? 2 to the power 3, the whole to the power 4 is what? I hope you understood. So like that, this is alpha to the power AB. So like that, both will come up, agree with the shared key without sharing any private details over the wire. This is called as Diffie-Hellman key exchange. This is what is used in TLS version 1.3. I hope it is understood. Right. So we are almost done. Next step is hashing. Next mechanism is hashing. It ensures integrity of the messages. Integrity of the message means message is not tampered over the wire. So Alice sends. What happens in hash is whatever be the length of your message, it will always be hashed to a particular number of bits. The hash or digest will be, say if you are using SHA-256 bits, then whatever be, even if it is 1 MB, it will be always be, the digest will be 160 bits, some unique random number. It will be mapped to a unique random number. So Alice will send this message and hash to Bob. Now what will Bob do? Bob will apply the same hash function on the message and Bob will get if he gets the same hash, same digest, it means that the message is not tampered. So look at this, here we are sending message as well as digest. Both will be sent. And the hash will be recomputed on the message to get the digest and these two will be compared. This is how it is done. So here our goal is to ensure only integrity of the message, nothing else, not confidentiality, not authenticity. Hope it is clear. What is the problem with this? E will simply replace this message with some random message and he will put his own hash and send it to Bob. The original message, E will drop it. Now Bob will compute the hash on M dash. It will be same. Bob will believe that the message is from Alice. Do you understand? This is the problem here. So for that, we use something called as hashed MAC. Here, both Alice and Bob will share a symmetric key. Alice and Bob will share a symmetric key. Okay, symmetric key. Now what happens is, Alice will take the message as well as the key, which is shared only with Bob, and apply the hash function, same hash function, to get the digest. Now this message and digest will be sent to Bob. He will not be sent over the wire. Do you understand? He will never be sent over the wire. Only the message and hash will be sent. Now Bob will apply the same hash function on the key and the message. And he will get some hash. If these two hashes are matching, what does that mean? Message has not been tampered and the message is from whom? Message is from Alice because Alice only has that same key. Now, Eve cannot do anything. Why? Even if Eve sends some message, she doesn't have the key. So it will always be wrong at the other end. So this is hashed math. All these concepts are used in the TLS handshake. Okay, now I'm stopping with this. And I will also say one more thing. In public key crypto, there is one small problem. Everything has its own problems. So that just that one thing I will tell you. So I told you that every bank has public key and private key pair, right? This will be, public key will be sent to Alice. Sorry. Public key will be sent to Alice. Now the problem is, anyone can generate a pair of public-private keys. So what he will do, he will drop this public key, he will generate her own public-private keys, and he will tell Alice, see, this is the public key of the bank. And he will send her public key to Alice. So this public key replacement attacks can happen in public key cryptography. Now, how do we prevent this? That is using something called as certificates, digital certificates. So let's just go and visit Amazon. I'll show you. Yes. Sir. Okay, if you visit Amazon, okay, whatever. If you click on this, can you, over on the top, if you click, you can see connection is secure. Click on it's a TLS connection. Click on that. You can see certificate is valid. If you click on that, you will be able to see the certificate that is issued to the server, Amazon.com. So here you can see this is Amazon's RSA public key. This is Amazon's RSA public key, and this is digitally signed by someone. Can you see here? It is digitally signed by DigiCert Global Certification Authority. Okay, so there are some trusted central authorities whose public keys are all already there in our browser's root store. Our browser comes shipped with these trusted central authority certificates. Okay, so with this, what is DigiCert CA is doing is it is signing this public key so that me as a client knows that this public key in fact belongs to Amazon. You understand? This is how we prevent public key replacement attacks. I hope it is understood. If you want to see the root store, you can go to browser settings, privacy and security, manage certificates. You can just see on my browser. Okay, you can see here Chrome root store, and you can see all the trusted CA certificates there. So in our case, it was DigiCert. You can see DigiCert global root CA here. And its certificate will be here. Like that, it already comes shipped with the certificate. So we as a client can verify it. Okay. Now we are moving on to Wireshark. You can open that packet which I shared. So immediately after the SYNS in ACAT, you can see that from my source, my IP to the server, I'm sending a client hello message. Can you see? Do you click on this message, client hello? Can you click on the message, client hello, all of you? So there are few fields there in client hello. You can see that the client is sharing the highest version of TLS protocol that it supports. You can see it is TLS version 1.2. And then you can see some random number here, a random number, okay, and a session ID. Session ID will be there. This session ID from the client side, when in the beginning of communication, it will be 0 bytes. It will be all zeros. But for session resumption, you will be able to see some ID there. We are not going to the intricacies of that. So now we are starting with a 0 session ID from the client side. Okay, next what will be there is all the cipher suites that this particular client supports. Let me show it in the slides so that I won't overwhelm you. Okay, so first, every server has this certificate. Amazon has its certificate. Okay, certificate, it has its public key and it has its private key. This should be there for the communication to happen. Now, the client is sending client hello to the server, and in my client hello, this much of information will be there. Version is the highest version of TLS that the client supports. Then random number 32 bytes. The first 4 bytes will be the timestamp down to 2 seconds. If you want, I'll show that there. Then session ID, it will be 8 bytes, 32 bits, and cipher suites, which will be the list of cipher suites that the client supports. Okay, and also extensions. This is what will be there in client hello. And when should I stop? When should I stop, sir? Okay, so here you can see Unix time. So this for the Unix time, this is 16 that is the corresponding hexadecimal representation. Remaining, you can see 5C 02, that is the actual random number. That is the actual random number. This is the random piece, session piece at the end. So like this, from the client, we will have a random number. The session, we will have a random number. Okay. So here you can see, please listen here. These are different cipher suite combinations that the client supports. Elliptic curve, Diffie-Hellman ephemeral, elliptic curve digital signature algorithm with AES 256 GCM, Gallo counter mode. We will not go into that much details. And SHA for hashing. So all these things, confidentiality, authenticity, and integrity, all these three features will be ensured by the cipher suite. Okay. Now, next is, you can see something called as server hello. Can you see? Packet number 7. Packet number 7, you can see server hello. Okay. In server hello, same details will be there. So the client has given lots of options to the server. The server will choose the highest TLS version supported by both the client and server. Server is the one that decides which TLS version both of them will use. Client has given all the options. Now, the server will also generate a random number. Okay, random number. Then the server will generate a session ID, which will be now the session ID that will uniquely identify the session for the entire session. And the cipher suite that is chosen by the server will be there out of all the options that the client has given. Okay, and finally extension. So if you want, you can check it over there in Wireshark TLS version 1.2. Here you can see server hello random. This is the server random number. Server random number. First 4 bytes will be the time, Unix time. Then session ID. This is the unique session ID for the session. And you can see the cipher suite that is selected by the server. This was one among the suites that was proposed by the client. So like that, all these things will be chosen. Okay. Pointer. Okay. Okay, I'll rush up now. Okay. So once this server hello is completed, once this is completed, both of them will have few things. One is both of them will now agree on the TLS version. Here TLS version 1.2 because that is the highest supported by the client. Next, both of them will know the client random number. Both will know the client random number. Both will know the server random number. Both will know the session ID, unique session ID chosen by the server. And also both will agree upon the cipher suite. Clear? This much clear, everyone? Right. Next is the server will send the certificate to the client. Why? Server could directly send the public key here in server hello, no? Why certificate is required? To prevent public key replacement attacks. So it will send the entire certificate chain to the client. It's there in the same packet, you can check. It will be there. But I'm not going to that. You can check because of shortage of time. So that entire certificate chain will be there. From that, what will the client get? The client will get the authentic what? Authentic public key of the server. By verifying the certificate chain, the client will be able to get the authentic public key of the server. Do you understand? Because it is signed by who? A trusted central authority. So that certificate contains the public key of the server that this client will be able to get. If you want, you can check in the in that capture. Wireshark capture, same packet. Okay, are you able to see this? Certificate, this one, this record. Certificate, This is sent by the server to the client. I hope you understood. That record is there. So once that is completed, next what happens is the server sends server hello done, which is an empty record, saying that at this point, the server has nothing more to send to the client. So the first part completes. This much is it clear? Everyone? Next. Communication is from the client to the server. The client will send client key exchange. Here in this slide, what I've explained is the one using RSA. But day before yesterday, when I did the capture, there the cipher suite selected was Diffie-Hellman. So their key agreement is being done. Slight change will be there. But this I am explaining with RSA, key transport, RSA. Okay, so client key exchange will happen. Let's see. So in client key exchange, what happens is this client will choose a pre-master secret key. Pre-master secret key. Just imagine that some symmetric key. It's a symmetric key. Okay. Now what a client will do is client will encrypt this pre-master secret using what? These servers public key. Do you understand? The client will using HTTPS. Okay, I'll answer at the end. I won't finish. Okay, pre-master secret will be encrypted using the server's public key. So the client is choosing the symmetric key now. Choosing the key, encrypting it using the server's public key and sending it over the wire. Okay, 2 bytes. This is sent, this is encrypted, this is sent over the wire. Now, if the server is whom he claims to be, he has what? Server has what? Server has the corresponding private key. So the server will be able to decrypt the pre-master secret, and both the client and the server will have, at the end of this conversation, both of them will have the pre-master secret. Do you understand? Both of them will get the pre-master secret because this pre-master secret was encrypted using the server's public key by the client. All of you got it? Okay. Next step. So this is for TLS version 1.2. In the TLS version in 1.3, 1.2 also some Diffie-Hellman key exchange ECDH is used. So if Diffie-Hellman key exchange is used, what happens is that both of them will share public key materials to each other. There will be client key exchange, server key exchange. Both of them will share their public keys and derive at a common pre-master secret. No key transport will be done. Okay, it depends on what protocol suite is being chosen. Okay. Right. So this is how it will be. Handshake protocol, client key exchange, RSA encrypted pre-master secret. You can see over here. RSA encrypted pre-master secret. Okay. So once the pre-master secret is shared, okay, okay. Now what will happen is both parties will do something. They will both derive the master secret now. Both will derive the master secret. So this is how it is done. It will take the both of them will do this step. They will take the pre-master secret. Then they will take the string, master secret, the string, client random number, server random number, and hash it. Okay, these things will be hashed to create the master secret. You understand? So they will take the both of them will do this step. Both has the pre-master secret, master secret string, client random, server random. They will do something like hashing and they will generate this master secret. Next to this master secret, they will append the string key expansion, client random, same thing, server random, and they will generate 4 keys. These are the ones that creates the encrypted tunnel in TLS. Okay, what are created? Client encryption key. If AES is chosen, this will be AES 128 GCM is chosen, then it will be an 128-bit AES key. This will be client HMAC key. Say SHA-256 is chosen, then it will be a 256-bit key. Similarly, we will have server encryption key and server HMAC key. You understand? And if say CBC mode is used in AES. I know for those who haven't learned cryptography, it'll be too much, but there'll be something called as initialization vectors. Those will also be derived based on the mode that is chosen. Those will also be derived from this particular step. So all these keys will be derived. Okay. So there are two tunnels here. Two tunnels are there from the client to the server. Client to server, there will be one tunnel. Whenever the client is sending some data to the server, the client will be encrypting the data using client encryption key and hashing it using the client HMAC key. Hashing it, doing HMAC with client HMAC key. Okay. Server also has these two keys, so server will decrypt it. Similarly, when the server is sending something towards the client, server is sending something to client, server will encrypt using server encryption key and do HMAC with server HMAC key. So there's a two-way tunnel here. Got it? This is how it works. So we have completed it almost. Just two last steps. Finished message. Okay. So this, I'm not going to explain it. Client key exchange done. So at this point, both parties have identical session keys. They just have to verify whether all the records are shared in the correct manner. Both of them has the keys. Only verification step is remaining. Okay. The next step is change cipher spec. That is there in the capture. Later on, you can check. Change cipher spec. This client is informing the server from this point on, I am going to use the session keys and I am going to encrypt everything. You will not see anything in clear now. Based on the agreed upon session keys, everything now will be encrypted. Okay. Next. Okay. That is done. And finally, we have handshake, this encrypted handshake or finished message. Encrypted handshake. What happens here is client will take all the previously sent record, TLS records. So client hello, server hello, certificate, server hello done, client key exchange, hash it. Okay. And client will take this handshake hash, append it with master secret, client finished, and again do another pseudo random function, or let's say it's HMAC function to get the verification data. Now this is encrypted with the client set of keys. This is encrypted with the client set of keys. What is the point in doing this? Is suppose I am an attacker. Okay, I know that TLS 1.1 is vulnerable. So what I will do, or I know how to do TLS 1.2. Suppose what I will do is, suppose both of them can do TLS 1.3. What I'll do is, in client hello, I'll modify and send TLS 1.1. So the server will think that the highest that the client can do is TLS 1.1. So to prevent this kind of an attack, the client is saying these are the records that I have sent and I have seen so far. So that is hashed and sent to the outside. Similarly, server will do in the next step. Server will do similar kind of thing in server finished message. Server finished message. Similar kind of thing. Server will do and encrypt with the server session keys. This is the finished message in the server. From that point on, everything will be encrypted. Nothing will be seen. This is the TLS handshake protocol. So I don't think I'll get the time to show you how to decrypt it. But usually what we can do is, even this encryption we can decrypt. This packets we can decrypt and see all the post messages. If you want, I'll show that to you. But for that, we have to log all these session keys. All the keys that were generated, no pre-master secret, then client session key, client encryption key, client HVAC, all those keys, we will be able to log it in our machine. At client side, we are the client. We'll be able to log it. And if you provide that pre-master secret or the log file to Wireshark will be able to decrypt everything and give you then that point on, you'll be able to see all the HTTP requests, everything. So I'll simply show you how I've done that. So here you can see that I've visited my LMS. This is the capture that I did. Visited LMS. If I follow TCP stream, actually I have submitted my user ID and password there, but you won't be able to see anything because it's encrypted. So you can see that client, hello server, hello change size, cipher spec. After that, everything is application data encrypted. Okay, now I'm going to provide the key that I've logged. This, I'm sure Mahima madam will be making you do this, so you won't be missing it out. She'll be doing it. So now you are able to see get, post. Can you see post? I won't show this part because you will be able to see my LMS password. So here you can see the post request. Now it's all decrypted. New session ticket, certificate, verify, finished, all those things you can see. And you can see get and post and everything. Decrypted. Yeah, this Mahima will be making them. Okay, any doubts? Okay, sir, I'll check. It is enough to secure a commission. We implement additional encryption also to secure our website communication. HTTPS will help you create an encrypted tunnel as I have shown. So all the application data will be encrypted. Then those who are developing websites to prevent vulnerabilities, they will have to during the development, the programming, they'll have to do all those mechanisms to prevent malicious attacks on their websites. That has to be done. But this is all the application data. If you are using TLS, it will be encrypted using all these mechanisms. Any other question?
Any more questions? If online
one
participants are
more.
having, please.
Is there any way to break the hash code that is shown in Wireshark directly using algorithms? So I don't know which hash code they are referring to. Sai, can you specify? There are collision attacks against hashing algorithms. Can you specify what the question is? Which hash code you are referring to? Sai? The hex codes in Wireshark. As far as I know, for the hash code specifically, it's safe. Since it's encrypted, even the hashes, everything is encrypted. So it will be secure unless you have the keys, client or server side keys. Any other doubts from the participants here?
Excuse me, ma'am.
Yes.
It's done.
Okay, thank you so much.
Any
Thank
more
you.
doubts? Offline participants. Okay. Thank you, ma'am. Thank you for the insightful words. Next, I would like to welcome Dr. Gautam Ali, sir, Assistant Professor at Indian Institute of Information Technology, Kottayam. He has received his PhD degree from the Indian Institute of Technology, Kharagpur. He currently works in research areas such as IoT, edge computing and intelligence, privacy and security. His research works have been published in scholarly journals such as IEEE Transactions on Computers, ACM Transactions on Autonomous and Adaptive Systems, etc. We welcome you, sir, for the session.
Internet. Normally it is always connected, okay. But today I don't know. Yeah, it has come. Yeah. Like this computer I got from a store, so there is no problem. It works fine, but today I don't have charges enough. Just yeah. Email. Yeah. Yeah. Huh? Why it is it's okay. So thank you very much for inviting. Good afternoon, everyone who have present here offline, and also the students or participants who have joined online. So very good afternoon to everyone. So myself, Gautam Mali. So I'm faculty here working as assistant professor. So I'm going to talk about lightweight cryptography. Okay. And how many of you are, okay, only I think all of you are participant, external students. Okay. So you are only, okay, our PhD scholars. So how many of you here who are present physically? So how many of you know about cryptography, basic idea? You have only. What about others? No. You are all UG students or PhD scholar also? You are PG, MTech. Okay. So lightweight cryptography we'll talk about, but not in so much detail. But whatever we'll go through, that would be very much helpful to know about importance of lightweight cryptography and why we need. Okay, like today, you know that cloud computing is there. Cloud computing, like always we are talking about cloud computing, cloud computing. So if we talk about like IoT devices, okay, or IoT network, we know that a lot of information are generated in IoT devices. Those IoT devices are very small in size. And when the size is small and also they have some other resource constant like memory is small there, like RAM, ROM, whatever is there, that is very small in size. So they cannot store more information, and also for processing, they have very low computing CPU. Okay, we call it microcontroller. So microcontroller is just like computer, but they have CPU, memory, everything is there. But those are very low computing in capability. Okay, so that IoT devices, they are generating lot of information, and those information normally they are stored in cloud. So they have to send the data, and those data would be stored in the cloud for further processing to get some idea what is happening that particular monitored area. So to get that, earlier what people did, like long back it was server. In the server, like a particular people or organization will have a server. In that server, the data would be stored. Then cloud computing, when cloud server, cloud computing came on the time, they started storing data taken from this kind of small devices there. Then cloud computing has certain problem. What type of problem? Like if you store the cloud, if you store some data in the cloud, so response delay would be much more. To get result of something, the decision result or something, to get back it would be really time taking. So latency, response latency is there. And also while you are generating lot of data in a particular local region by IoT devices, so on the time sending those data would be really costly in terms of bandwidth consumption. Like they require a lot of bandwidth. So these are two major considerations are there. Like we cannot go for all type of application storing their data in the. So what is the alternate solution? Better to keep the data in the local region itself. In like not for processing, you can store there also little bit, and for processing, and also like no need to send them all the data to the cloud for their processing, getting the result back. No need to do that. Rather, you can keep the data in the local devices itself, and there you can process it at certain extent. But if we want to do like some kind of high competition, little bit more competition like image related data or something else, on the time computation would be higher. So on the time, instead of going cloud, there is also intermediate server. We call it edge server. Edge, EDGE, edge server. There we will have the intermediate computation. So we will not go to cloud if there is necessity. Otherwise, like either in the edge devices or IoT devices, the computation will take place, or in other cases, we will take help of edge server, which is very near to that particular local region, monitor region. So when we have all these kind of IoT devices, like here lightweight cryptography we are talking, and that discussion would be from the perspective of IoT network. Like IoT devices, they are very small in size, and also they have those constant like energy constant, battery constant, energy or battery constant, then memory, then computation constants are there. So those devices, though we have the like we want to do carry some kind of computation there, but yes, any type of tasks we cannot compute there. So we are talking from the perspective of IoT network, IoT devices, but at the same time there are problems like we are not going to perform computation in the cloud by sending the data. Rather, we'll try to focus on local computation. So there comes this lightweight cryptography. Like security is there, so that is why lightweight cryptography comes there. So here, when we are talking about lightweight cryptography, sometimes we'll discuss some other relevant topics, rather some other relevant discussion we'll have, and we'll see also that what are the other type of attacks are there, what are the different countermeasures are there, security countermeasures are there, and finally we'll look into that, yes, how we can make the security with the help of lightweight cryptography. We'll move toward that. So that would be our discussion in this lecture. So let's move. We'll see some of the IoT application here. Some of the IoT application we'll see here. So like IoT nowadays, IoT devices or IoT network is everywhere. Everywhere. Like if you consider, for example, smart home or smart building, okay, then agriculture, then health monitoring. If any application, if you consider, even for example, food supply chain, like food delivery of the foods, okay, you know that RFID tag is used there. Okay, we can keep track of that. Normally, this kind of like food delivery is not there, but if we want to deliver some other stuff, like some electronic gadgets or something purchased in Amazon, so we have some kind of tracking capability there. So some other small devices are associated there, kept there, so that we can track also. Okay, so these are different applications that IoT can have. IoT devices can make it possible, and there comes some role, okay, or prominent role of IoT devices. Like here, IoT is there, so it can have the capability to connect anything, any device. Anything means Internet of Things, means anything, any device. It has the capability to connect anything, anywhere, anytime. Okay, like they have to have that some kind of network provision there. Then they can easily be connected to the people or some other devices like router or gateway or some other device. At this point, they can be easily connected. So it has that capacity, and that is why it becomes like sensing, actuation, whatever we call it. It becomes such utility. Okay, and as a result, that all these different type of utilities are there. Like we can consider health monitoring, we can consider food supply chain, we can consider smart farming, whatever. These are coming as utility service to us, and IoT becomes their important, okay, key factor. IoT means IoT devices. And what it does, like here, cities are becoming smart, and in that smart city, there are many different things are embedded, and they may communicate to each other. In certain situations, what may happen, like we can have, for example, refrigerator, we can have washing machine. So they may have, for example, internet connectivity. They can be connected to people, okay, so that you forgot to switch off them from your mobile or some other utility, you can switch off it. With the application, you can switch it off. So that provision is coming. Okay, nowadays, we don't have that facility. Common people we don't have, but many ways these are done also. Okay, you have heard in some research paper while going through it, you have heard of. So those applications are till now. Okay, already those are in common practice also. Though it has not reached to all people, but it is used. So in like refrigerator and those different IoT devices are there, and they can communicate to each other, and they can talk to each other. They can decide also. They can have some kind of computation capability, and they can decide also by themselves that yes, after running some kind of lightweight machine learning algorithm also there, they can decide. They can make decision that what to do. Like better to switch off now because there is no other activity, so switch off. They can make that kind of decision also. Just for example, you may consider that. So now, when this kind of like connection to the people, everything is happening, how they may happen? It may happen via internet, means network, through network. That is possible. And when that connection becomes severe due to certain reasons, okay, there comes the problem. Means what I am trying to say that communication is always through internet, and when something severe issue happens there while via internet, there comes the role of the security. Security plays important role there. Like we have to think about security. Like we are getting all the services by IoT devices or IoT network, but sometimes some data we have there, and that data has some kind of importance, and we have to make it secure. So there comes the role of security, because it is connected via internet or network. So there comes the role of the security. Now, when we talk about the security in IoT network, what are the different devices we have? All are small devices. They have energy constraint. They have memory constraint. They have, for example, computation constraint. All these different constraints they have. Like here, some example you can see, like RFID, which is like you will find in most of the like application, you will find RFID nowadays going to be used there. Okay. Then we have sensor nodes. You have heard of sensor or sensor nodes. Then we have smart card. Then we have some kind of microcontroller also. Like they are just mini computer, but they have some other like constant. But they have capability, like processing capability, CPU, RAM, everything is there. Or ROM memory is there. So that is there. Now, if we want to apply some kind of conventional algorithm there, if we want to apply there in this low configured devices, that would be problem. Like those conventional cryptography algorithm like DES, you just heard symmetric key cryptography or asymmetric key cryptography, if you want to run there in those low configured devices, those resource constrained devices, it will create problem. What are the problem? As we discussed, like they will consume more energy. That will create problem for those devices. They will, like the memory is there, you cannot, for example, run bigger program there, because these are all programs. You cannot keep the entire big program there, large program there, because they have memory constraint. And also, like when they will compute, okay, like these are algorithm programs. These are algorithm programs, so they will compute. When they want to compute it, it would be really large latency would be there, computational latency. Like, for example, we have considered that we have, for example, 3 lines of code. 3 lines, only 3 lines or 4 lines of code is there. So whatever time it will take, if we have 1,000 lines of code, it will take more time. That is normal. For example, each line will have some computation. Then we come across, for example, 1,000 lines are there. Then based on different like algorithmic approach, again, there is also changes in that total time complexity. That is different, but normally we have simple instruction there, simple statement, C programming like statement is there. And if we have, for example, 3 instructions, it will definitely take less time. And if we have 1,000 lines of code, it will take larger time. So in these small devices, we have that problem. Like we cannot run a conventional cryptography algorithm because they have 1,000 lines of code. Okay, those are larger in size. Size also means lines of code are more. Okay, to achieve that security performance. That is the problem. So there comes the lightweight cryptography. Like it provides certain benefits over the existing cryptography algorithm. Okay, like data encryption standard, advanced encryption standard, or RSA algorithm, asymmetric key cryptography. So they provide advantage over them. Okay, because these 3 important factors are there. There may be some other factors, but these are 3 important factors, like energy, memory, and computation latency. These are 3 important factors. Now we'll look into that how they are defined. Okay, little bit different. Like if we go for example, conventional cryptography algorithm, okay, we can run them like in normal computer, in server, desktop. Normal computer means desktop we are talking about. In server, we can run them. Then even like nowadays, that mobile device that we have, we can run them. But there are also some other mobile device, we cannot run any program. So mobile device is also considered as IoT device, okay, kind of IoT device you have heard of. But yes, mobile device has so much computation capability, they can run traditional cryptography algorithm. They can run. They can be able. Okay. So mobile device is considered in that particular category that yes, they can run conventional cryptography algorithm. Tablet is there, some other devices are there. But when we talk about, for example, this type of devices, okay, like RFID sensor nodes, which have resource constant. If we want to run conventional algorithm, so they will consume more energy. That computational delay would be there. So there are differences. We cannot run those conventional cryptography algorithm in low configured or resource constant devices. That is the problem. Here some examples are there, like in IoT devices, microcontroller is there. Okay, IoT devices, microcontroller is there, just like computer, but with low configuration. Here, some information we have provided, like microcontroller means CPU size. For example, CPU size in the sense, registers are there. Okay, in the CPU registers are there. The register stores the values. Before actual computation by the LU, in the CPU, you know that what are the different components, like register would be there, cache memory, that kind of stuff would be there to store the value. Then we will have register bank. Some register would be there, and predefined instruction would be there. Predefined instruction, like there is no as such compiler, those kind of things, but yes, similar stuff is there, compiler or similar stuff, or assembler, we call it assembler, that type of program would be run there. And this type of microcontroller support only limited number of instructions. Like when we talk about assembly language, it has limited number of instructions supported by that particular assembler. It cannot go beyond that. Like when we talk about compiler, that you are using for running, for example, C language or Java language, it has to follow certain syntax. Those are defined in that compiler, in that particular programming parlance. You can't write anything arbitrarily out of that compiler. So here also we have assembler. You can call it compiler. It's okay, fine, because it will just compile and it will convert to corresponding machine level language, zeros and ones, and that would be computed by LU for operation. Okay. So here we have that. No? What is happening? Only by this? Okay, sorry for interruption. Okay. So, yeah, thank you. But it is not there. Control, it should be there now? No. Okay, fine. Let's move on. So this microcontroller is there. So the size we are mentioning, this is the size of register. This is the size of register. Okay, like some important registers are there. For example, accumulator is there, stack pointer is there. Those kind of stuff must be there. Okay, like have you heard of MIPS? Any assembly language have you heard of? Ever come across MIPS processor? Have you heard of MIPS processor? MIPS assembly language. Have you seen assembly language in your course curriculum? You have some idea? Okay, some of you have idea. Yes, thank you. So you know, you have some idea, and there that register like accumulator or stack pointer or some other predefined registers are there. They are of fixed size. So here I have considered this size like 8-bit, 16-bit or 32-bit controller means the register size. These are defined by their register size. They are that. And which is easily available and with less cost, that is 4-bit microcontroller. When we talk about 4-bit or 8-bit microcontroller, there the number of instructions would be executed. The corresponding assembler is there, so number of instruction would be less in number, like supported by that particular embedded system or microcontroller. It would be less in number. Now, if you want to, for example, convert that conventional cryptography algorithm to the corresponding assembly language to run there, so it would be very large number of instructions. There comes the issues. The challenges come there. So if you want to run that large number of instructions supported by that limited number of instructions, so you have to have 1,000 lines of code, okay, in that assembly language. If you want to run there, so it would be computational, it will incur computational latency, it would be more energy consuming, so those problems come there. So traditional cryptographic algorithm you cannot run in these IoT devices because of this, like whatever computing system we have in these IoT devices, they have this kind of constant. So if you want to convert this traditional cryptography algorithm there, okay, with the help of assembly language, so it would be huge, large number of lines of code. And if you want to run them, they will, for example, stop or hang. They cannot get the result finally. That is the problem. And also latency would be there. So that is why we are going for lightweight cryptography. That is why we are going for separate cryptography algorithm, lightweight cryptography. That is why it is important. Now we'll look into, like we are talking about cryptography, why it is needed. So why it is needed? So better to have a look about different type of attacks. So all the attacks that we have, we categorize into two main categories. One is passive attack, another is active attack. By passive attack, you can understand that yes, they are not going to harm at major extent. They will just have information which is transmitted between the authenticated sender and receiver. They will have that, they can monitor, they can have that message, but because that is ciphertext, okay? Like when we are talking about security or whatever message actually we transfer, like either email or for example, WhatsApp or some other application, all are encrypted message. Do you know, guys? So there are some kind of cryptography algorithm associated with that application. They convert it into some kind of gibberish or some kind of other values that other people, if they receive that message due to certain system failure or node failure, this kind of computer failure, they cannot understand the message. So we call it ciphertext. So always there are, with each application, there are some cryptography algorithm. They convert the plain text, whatever you are writing or whatever this kind of nodes are transferring or transmitting, they would be converted to the corresponding ciphertext, and that would be completely like not understandable by others. Only the intended receiver who will have the corresponding key to decrypt it. So after decrypting, they can understand that what is the meaningful message there. Otherwise, it would be completely not meaningful. Okay. So in case of passive attacks, so there is no modification of the message. They will simply take the message. They can have that. If they have some key something, they can retrieve the original message. That's all. In case of passive attack. But active attack is very dangerous. Very, very dangerous. Like all different problems, okay, like for your message that or for your data, financial transaction is much more secure. Sometimes we have some data, okay, you like to say like some kind of bidding or something is there. So those are very secure, okay. So if adversary may get those kind of information, having the corresponding key, which can help to decrypt the message, then it's okay. They can have that. But in case of active attacks, it's not only getting the message, it's about doing beyond that. What is that? Like we'll go through detail about different type of attacks, some details, but a lot of different type of attacks. Why we are considering this attack discussion? Because when we talk about any security mechanism or security algorithm that you are proposing, that algorithm will not work for all different categories of attacks. So you should consider some attacks that yes, these attacks, against these attacks, my algorithm works fine. Cryptography algorithm or security algorithm works fine. Your algorithm, design algorithm is not going to work for all different categories of attacks. So better to have some idea that what are the different type of attacks we have and how our proposed lightweight cryptography algorithm works there. So we are going to discuss that. So it is active attack. Active attack means modification of message, replay of the same message, Then sometimes we can also put or place replica, okay, of the same device, okay, kind of replica we can place there in the network. All these different type of attacks may happen, and another is like denial of service. So we'll talk about that, what is denial of service, okay, what are the different type of attacks are included there, belong to that particular category. We will discuss that. Denial of service, normally what we consider, like, I will not accept that yes, you have sent me something. Normally we consider in that way, but it's not exactly the same about denial of service. There are little more about denial of service. Normally we consider in that way, like you are sending something, like you have sent message, I am telling no, I have not received the message. So I'm telling the no. So that is considered as denials of service in abstract manner, but there are many more in this particular category of attack. Let's go through different type of attacks. So here the first category is about malicious injection attacks. So all are about, not all, most of them are active attacks. Some of them we'll discuss about passive attacks. So here first is malicious injection attack, means we are going to inject some kind of malicious nodes or malicious devices there in the network. So first category we are considering it is node replication. By this name you can understand that we will have access to a node in a trusted network, then we will make replica of the same node. And we will later on place those replica nodes in that particular trusted network, so that they can hamper. So one replica may be more than one. We can place there. It can be done by the adversary. Adversary means enemy. It can be done. So now they will start hampering the normal operation of the network. How? Like they receive some message, they can discard, drop that message. They can misdirect, like they are supposed to go in a particular direction, they are directing it to some other direction, other node. So in this way, all these different type of normal operation of the network would be hampered in case of node replication attack. Here, only replica of the same node would be placed in the trusted network. There is another camouflage, like a particular like fake node would be injected there. And it will perform in the same way, like node replication attack, the way it works, this fake node, because we are injecting a fake node there in the trusted network, it will work in that way. We call it camouflage attack. Then we have, very important, this one, side channel attack. So here, they are not going to make replica, they are not going to like a copy of the same node, no, nothing, or some other way. What they are doing, even they are not taking the original ciphertext transmitted between sender and receiver. What they are doing, instead of intercepting the original ciphertext transmitted between sender and receiver, they are capturing some side channel information. What is meaning of side channel information? Like when we are sending some kind of data, so like some electric power would be there, some power would be there, okay, power consumption would be there, or some kind of power would be there. We call it receive signal strength index, okay, receive signal strength. So based on that, they will get some information, they will get some radio wave, for example, radio, they will get some information, and from that information, they will try to correlate with actual data, and they will get idea about the data, that yes, this is the data. You understand that it is not possible apparently, but yes, attackers, they are so much advanced, they are so much intelligent, they can do. So this particular attack is very important, like okay, from adversary point of view, enemy point of view. So this is another kind of attack. There are many other ways they can do that, okay, all information are there. So side channel attack. Then we have authentication authorization attack. Here in this case, like some kind of password dictionary or credential dictionary, the adversary will use, okay, and they will crack into the authentication of the system, and then they will get the data or whatever they are looking for. So they will get. So here to provide the security, these are some of the very well-known authentication protocol is used. Like you just came to know about TLS, transport layer security. Details discussed. Another version of the same is secure socket layer. Then we have Wi-Fi protected access also. In many places you will find that WPA, like in your laptop also, I think you will come across that particular name. So it is there. So their authentication and authorization protocol. Okay. Then we have jamming attack. Sometimes what happens, like that kind of passive attack, this one, it is passive, it belongs to passive category. So what happens, like they will keep a note, okay, malicious note in trusted network, and they will continuously send some kind of fake message or spurious message with high power, so that if some other nodes want to send their data, these spurious messages will consume the data. Fake messages will consume the bandwidth available in that network. Now, that trusted network or benign nodes in this network, they cannot send their data because bandwidth is consumed by those messages. So this is another way, like adversary can hamper normal operation of the network, but they are not going to change any data there. Okay. Then we have distributed denial of service. As I mentioned that, yes, normally we consider as like, I'm not agreeing with whatever you have sent. Okay, like email you have sent, you are telling that you have sent email, but I'm telling no, I have not received that email. So in that way we consider, but here we have many more, like distributed denial of service in this particular attack. Like first one is outage attack, then we have like sleep deprivation, and third one is like battery drain. More or less these three, though three different names are there, but you will find that there are huge similarity between them. The first one, outage attack, in this particular attack, what happens that normal nodes in the network, they cannot perform their operation. It would be hampered. Okay, we call it outage attack. Like they are supposed to do some operation in the network, like sending, at least sensing some data and sending the data. Okay, in case of sensor network. So they cannot do that, perform that normal operation. Similarly, in case of like sleep deprivation, some kind of genuine message or legitimate messages would be sent by the adversary continuously. And the nodes in the trusted network, benign nodes or legitimate nodes in the network, they will continuously busy replying those messages. So automatically what will happen, that they have some kind of battery constant or that kind of stuff, problem is there, constant is there. So their battery would be drained replying those kind of fake messages. And those fake messages should be legitimate message. Okay, they have to answer. So that is another problem, very major problem. We call it distributed denial of service. Similarly, battery drain. Okay, so the battery would be drained of those nodes by replying some kind of message, like this kind of message. And this is another matter. Then physical attack, as the name implies, like adversary will have access to the physically to the nodes. Okay, then they will change the circuit. Okay, they will do that. They can have access to the operating system. They will modify their, okay, they will have information of the cryptography material. All this may happen. So this comes under that, physical or attacks or tampering. Then we have eavesdropping, like this is purely like passive attack, like simply the adversary will, adversary means adversary node, okay, they have the capability, okay, not adversary directly. Don't remember, like no people would be there. Some kind of device will like look after the data transmission. They will monitor the data transfer, inspect the data transmission, and they will capture it. Okay, some device has the capability, like whatever we are talking about, all devices which are intelligent, like they have computing capability, they have thinking capability at the very beginning, like we shared that. So they have just like the intelligence, okay, just like human being, but not exactly like they can't overcome us, but they have much more intelligence there. Nowadays, the devices available, they have much more intelligence, okay? Like if we are able to run machine learning algorithm in those devices, so they can make decision also, okay? So that are there, okay? We have made it. So now that particular eavesdrop attack is there, like simply they will eavesdrop the communication and they will get the information, okay? So similarly, we have replay attack. What it does, like adversary node will capture some information, okay, transfer between sender and receiver. Later on, they can replay that previously captured message during real-time data transfer. So they will hamper, okay? Like just simply they will hamper, they will consume the bandwidth, they will consume the energy of the other nodes, okay? Then we have routing information attack. Different type of routing information attacks are there. Some of them like black hole attack is important. Then we have civil attack, hollow flood attack. Different attacks are there in case of routing information. So what happens in this particular category, like when we talk about these small devices, they establish a routing path from source to destination. They establish a routing path, like multiple nodes should be there to send the data from source area, a particular area, source area to the destination. Like destination, for example, a server, for example, or some other nodes. We consider it as having some better computing capability. Okay, so or some other nodes, normal nodes. Then from that node, the data would be sent to the edge server like that. Okay. So routing path should be established. When routing path would be established, some of the nodes, that is malicious node, would be part of that routing path. Then they will hamper the normal operation of the network. Like how they can hamper? Like they can simply drop the message. Whatever information is coming to that node, they will drop the message. They can misdirect. Okay, it should go to the next node in the routing path, but that particular node, malicious node, which is now in that particular routing path, they can simply misdirect, redirect the message to some other destination like that. So these are different category of attacks which can, like, bring some changes in the routing information. It may be data during setting of the path also, they can create some problem. Like here, like I can consider the example of black hole attack. Like by the name, you can understand that yes, it can just consume all the information coming to it. It can just vanish the information, okay? So here, a particular malicious node tells others that yes, I have the shortest path toward destination. So others will start sending the message to that particular node. And once it receives the message, it will just take it with it. Okay, it will not forward further. Then they can do some other attacks there, like modification of the message, okay? Then some information would be changed there, okay? Source destination may be changed. All these different type of attacks they can start doing there. So this is about that. Now we'll talk about some solution also. Okay, like different attacks are there. These are not all the attacks which are present in our, okay, like in our world. These are not all attacks covered here. Like perhaps some of you have heard of zero-day attack. Okay, zero-day attack. Okay, you guys know that, but other students, I have doubt. So zero-day attack is there, collusion attack is there. There are many different type of attacks. They are different from each other. These are some of the attacks which give you idea while designing some algorithms, okay, cryptography algorithm or cipher algorithm. You will get some idea. You should have some idea about different type of attacks. Okay, that is why I kept it, but there are many more different categories of attacks. These are not only that all different type of attacks present in network, okay? So here now we talk about security countermeasure. So when we talk about security countermeasure, cryptography is very important, but besides cryptography, there are some others also which may take part to make your system, like multiple IoT devices there in a particular network. We call it one network system. Okay, we call it system. So here we have packet filter for security countermeasure. Okay, packet filter is there. Very simple mechanism this particular security countermeasure follows. Then we have firewall. Firewall, I think all of you have heard of. Like in any computer, firewall is there, any computer, but normally that firewall that we are talking about. So this is about, for example, a particular network is there. You have gateway or that kind of edge server is there, because we are talking about edge computing. Sometimes we are using that edge server, edge devices, we are using those terms, okay? So edge server is there. Now in the edge server, you can set up firewall or this kind of packet filter so that some malicious information cannot enter your network. Like, for example, you don't have insider attack. Like active attack, those we discussed, okay, most of them, like node replication attack, or where the adversary will have access to the nodes in the trusted network. If that kind of insider attack is not there, then you can prevent by setting up packet filter or firewall to detach your network from rest of the world. There are chances. So you can use firewall or packet filter, those kind of system you can use in that edge server. So that this firewall, for example, similarity is there because firewall also it filters packet. Okay, based on its content, it filters packet, and a firewall it looks after that incoming outgoing packets continuously, and based on certain rules satisfied or defined predefined in that firewall, they checks the content of that particular message and they simply drop, or they can like drop that. Okay, like they don't allow to enter that particular message inside the network. So like that, they work in that way. So here key function of firewall is traffic inspection. Then we have traffic filtering, access control, monitoring, logging, all these different functions are provided by firewall. So in this way they work, but firewall cannot be like placed or cannot be employed there in IoT devices. That is not possible because it is little bit like large program we can consider, okay? So these are different security measures. Then we have intrusion detection system. It works in a different way, like it continuously monitor network operation combination link. Then if there is, for example, any suspicious activity, it suddenly alarms others, that gives alarm that yes, some suspicious activities there by sending some kind of alarm message. So in this way it works. Then comes, which is our discussion actually today, cryptography scheme. So this is the most strong efficient mechanism to provide security countermeasure. That is our discussion. Like I discuss whatever, those are very preliminary. We should know, okay, when we go through like cryptography security, okay, on the time we should know that what are the different attacks, why we need lightweight cryptography, what is the necessity there. We came to know about that, but now we'll look into the actual discussion of this lecture, okay? So cryptography scheme. So these are very strong and efficient mechanism, always we know that, but these small devices we cannot apply the traditional cryptography algorithm because already we have discussed. So there comes the role of lightweight cryptography. So when we talk about lightweight cryptography, so one faculty is there here. So she's teaching lightweight cryptography. She knows more than me, okay? So there are many different type of lightweight cryptography algorithms proposed over decade, okay? Different type of cryptography algorithms are proposed. And here, why they are needed, we discussed about that. We are not going to the discussion of the same. Here, we have considered some of the lightweight cryptography, okay, which in those direction already many algorithms are proposed. So first one is lightweight block cipher. In traditional cryptography algorithm also we have block cipher, but they are not lightweight. There are certain consideration. Those considerations are made here to make it lightweight, okay? So lightweight block cipher we have. Then similarly, just like conventional, we have lightweight stream cipher, we have lightweight hash function, and the final one that we are discussing, that is elliptic curve cryptography. The last one is very important, okay? Like they come also with traditional cryptography algorithm, but later on when these IoT devices came into, on the time its use has been much more. Okay, people always are using elliptic curve cryptography because they have lesser computational delay. Okay, so that is why it is very much important. Like most of the lightweight algorithm, if you go through research paper to find the details about that, you will find the use of elliptic curve cryptography. Okay, always like they are using elliptic curve cryptography. We'll see some of them. Okay, some information about elliptic curve cryptography we'll go through, okay, that how it works, its working principle. So let's start with lightweight block cipher. It is completely theoretical, you understand, okay, a lot of information I am sharing. So completely theoretical, there is no practical exposure here in this particular lecture. So are you finding okay, guys? It's okay. Okay, anyhow, it is okay whether it is or not. Okay, fine. So lightweight block cipher and lightweight stream cipher, these two particular lightweight primitives, they belong to symmetric key crypto system. By symmetric key crypto system, you know that because in earlier lecture you have gone through, okay, that idea, like same key used for a particular key is used for encryption and decryption. Like a single key is for both encryption and decryption. That is why it is called symmetric. In case of asymmetric, like elliptic key cryptography, it belongs to asymmetric key cryptography. Why? Because there are two different keys for encryption and decryption. So that is why asymmetric. Symmetric because a single key is for encryption decryption. Asymmetric means two different keys are used for encryption decryption. One of them would be public, means other people may know, as the name implies. So that is why it has also another name. We call it public key cryptography. Instead of asymmetric, it has another name. We call it public key cryptography. So block cipher, lightweight block cipher, and lightweight stream cipher, they belong to that category. Symmetric key cryptography, or symmetric key cipher. While ECC belongs to asymmetric because ECC has two different keys. Okay, one is public, another private. And hash function, though we are talking about hash function, it is used for some other purpose, but not for encrypting and decrypting. What is the purpose? Anyone has any idea about hash function? Hello? Do you have any idea about hash function? Lightweight hash function we are going to talk about. Any idea? No. Okay, fine.
Integrity.
What is the idea about that hash function? We'll come to that. Okay, when we'll come to that particular slide, we'll talk about hash function, how it works a little bit. I have very limited information in the slides, but yes, we are discussing during this, okay? So you may get some idea, but all are theoretical, okay? All are theoretical, completely information. Huh? Figures are there, some figures are there sometimes, but not always. So lightweight block cipher, so data encryption standard that we talked about, okay, symmetric key cipher is variant is data encryption standard lightweight, DESL. L stands for lightweight. It is variant. What they have done, like when we talk about any encryption mechanism, there are certain steps. What are those steps? For example, first is like when we talk about block cipher, you have big message like one PDF file, or for example, 100 PDF files are there, all message, okay, all sentences. So that sentences should be encrypted with the key. So how you can encrypt? Key size fixed, for example, 128 bit, and everything would be considered in terms of bits only. Okay, like how you can convert the text into bit number. For example, numbers are there, maybe sometimes we have alphabet letters. How you can convert? By using their ASCII value. Computer works in that way. So similarly here also, you can think in the same way. So they would be converted to either number, numerical values, any character or alphabet letter would be converted to numeric value or into bits. Finally, bits. Okay, computer works only on bits. So they would be converted there. That is why always you will find that key size is 128 bit. They are not telling that yes, it is 3 digit. They are 128 bit or 256 bits, like that. Okay, finally, because we are dealing with computer always or similar type of devices where only bits are means on the bits it performs operation. So here in this case, when we talk about, so you have, for example, 20 pages of PDF file, and how you can encrypt those 20 pages, all sentences in by a key. How it is possible? Means you are going to make corresponding ciphertext. It is not possible. So what this block cipher does, it divides those 20 PDF files, sentences into block of certain fixed size. Like for example, 64 bit or 120 bit, like that. Okay, they will make different blocks of fixed size, and on those blocks, the key would be applied. Like some kind of operation is there, key would be applied, like some mathematical operation, okay? Simple mathematical operation, like it is about a value is there, 2, for example, numerical value 2, you are adding 4. Okay, so instead of 2 in the original message, it would be now 6. Then another letter number is there, for example, 5. Again, you are applying, for example, 4. So it would be 9. So in this way, original message would be converted into some other message. Now original message has a particular coherence between them, a certain kind of relation between them to make it meaningful. Otherwise, it would not be meaningful, like we can't understand that. So when you are converting them, they would be completely not meaningful. Those we consider as ciphertext. So in this way, like we'll have breaking of larger text into smaller blocks of fixed size, and each block will apply the corresponding key so that it will change to ciphertext. The ciphertext would be transferred over in secure channel or over network. So here comes that block size. Okay, block size, we can reduce it. Key size, another important, to make it lightweight. I'm talking about lightweight. To make it lightweight, we can consider key size, reducing the key size. Like we have normally 128-bit key size or 256 key size. If we can make it, for example, 60-bit or 80-bit, perhaps it would be improvement. So we can reduce key size. In data encryption standard, we have a lot of different rounds. Like when we get final ciphertext, the operation I mentioned, like simply just shifting the values, that normal operation is not done in actual cryptography algorithm. There are much more complex internal steps there. Like we call it rounds or different stages. In each stage, from the original key, there would be different subkeys. Those subkeys would be applied on that intermediate ciphertext multiple times in different rounds. Means one time, but as we have multiple rounds, so multiple times it would be applied. Finally, we will get final ciphertext. So it would be completely changed from the original plaintext. You are getting idea. Perhaps you can see that, okay? You can observe that. Yes, perhaps in this way it is going to happen. I don't have any example here, any slides I don't have, but I'm telling theoretically, perhaps you are getting, guys, okay? I'm assuming that, okay? Okay, pardon me if you don't assume, you are not getting. So in this way it happens. Now the rounds, number of rounds, if we can reduce it. Like we have many rounds, if we can work on reducing the number of rounds. Like in data encryption standard, we have initial permutation or initial round, final round. That is removed in data encryption standard lightweight. Lightweight version, that is removed. Then subkeys generated, those subkey also would be of smaller size. And also there is a particular algorithm creating different subkeys in different round. So that algorithm also would be made very simple so that it can be not much more time taking, not much more energy consuming, like that. So these are some changes made in the traditional block cipher to make it lightweight. So in this way it works. So some examples are there of lightweight block cipher, like present is there, very first one, okay, present, the first one, okay. Similarly, Simon spec is there. These are not only that these three lightweight block ciphers are present. There are many other proposed block ciphers, okay, but they have been used, okay, in IoT devices. They have been used. Okay. These are very popular, famous. These are. Then we have stream cipher. Okay, the same discussion is there, that how we have made that lightweight block cipher by changing in rounds, okay, number of rounds, then subkey generation, in every key size also, okay, there we have made changes so that we have got lightweight block cipher, okay. Then we have lightweight stream cipher, as I mentioned that, but I like to give some idea that how stream cipher works. In case of block cipher, we have known that original message will be broken into smaller blocks. Then on each block, we will apply the key. In case of stream cipher, its working principle is different. Like what would be the size of the message? The size of the key would be same. That is the problem in case. in this case, stream cipher. But yes, the researcher, academicians, they have made their effort to make it lightweight also. It is also very popular, okay, primitive, security primitive, stream cipher. And like that key generated, okay, by streams, like some mechanism is there, some kind of hardware is also used, polynomial, we call it polynomial also used to represent that hardware. I doubt that you have heard of or not. So we call it linear feedback shift register, okay, representing that particular polynomial, or non-linear feedback shift register. You can combine them, registers are there, like flip-flops are there, okay, to create this kind of key. Security key. So they are there, and lightweight stream cipher is also there. These are two examples, like grain and trivium. Okay, two examples I have considered. These are commonly used, means people have used earlier. Okay, now always there is update in this journey. So people have come up with some other stream cipher, definitely lightweight stream cipher. But earlier they proposed like grain and trivium. These are till now are used in IoT devices. Maybe, okay, I don't have that information, but these are very famous, grain and trivium. Trivium has the problem that it has only, suppose 80-bit keys. Key size is 80-bit. Okay, these are some information. Now we'll move to hash function. As I mentioned that hash function, no idea about hash function, how it works. Yeah, so nice. Okay, I just look for that word. So why hash is needed? Like three important factor, okay, for security we need. We call it CIA triad: confidentiality, integrity, and authentication, or availability. Sometimes we call it availability also. So integrity hash function, with the help of that, we provide that integrity of the message. By integrity, what we mean? That we are telling now that we can modify the message, adversary can modify the message. So if we apply hash, the adversary cannot modify the message. But simply applying hash on the original message and appending with the message will not provide it. It has much more steps. Okay, what is that? Like we secure that hash value also. And when we secure the hash value, we call it signature. Okay, those are terms we are not going to discuss here. So like when we send any document to some other party, we sign by our signature, then the person who is receiving, looking at my signature, they can understand that yes, it is coming from some genuine party. So here also hash would be made of the original message, then hash would be encrypted with private key. Another way, okay, private key would be used to, because here that signature, it denotes the origin of the message coming from. So signature is always created with the help of private key, not public key. In other cases, message encryption, in case of public key cryptography, message is encrypted with the public key. That is different. Signature is different. Okay, so in hash function, what happens? You have original message. We will create message digest with the help of hash function. We call it message digest, smaller in size, but you cannot get back, never. Okay, it has certain properties of hash function. It follows that you will never be able to get back the original message from the hash value. So once you get the hash value, now it would be very small in size. How it is made actually? So it is not just simple like converting something. Rather, we have compression algorithm there. By compression, you understand that you have large message, you will compress it, you will make it smaller, okay, size. So compression algorithm is there, and iteratively it is done. Like not in a single step, rather we have multiple stages there. In multiple stages, it would be compressed again and again. And actual message is not considered at the very first moment. Every time that each iteration will have part of the message and will get the message digest. Now you can understand, you can visualize that how complex this mechanism. Okay, like some idea, whatever final value, hash value will get, you cannot get back the original message. Never it is possible. Okay, because we have done multiple times the conversion or compression to get the final hash value. It will come also as a message, and that would be appended with original message. Now, if we go for conventional hash function, like Markle-Damgard is there, so all hash function work based on that Markle-Damgard. Very popular hash function is there. It follows that multiple compression. Now there, if we apply that conventional hash function, it has, as I mentioned, that multiple iterations are there, means multiple internal states are there, means internal values are there. So if we go for that, internal state size would be larger. If we go for conventional that hash function, so it will create problem again, like energy consuming, all this problem will come there. So we cannot use that. Instead, we have also lightweight hash function, like these are very popular, photon, quark, and spongeant. And they have reduced there, okay? That basic functionality, they have worked something and they have changed it so that it would be lightweight. It would not be so much energy consuming, so much computational delay. It will not take. So they have worked in that. So this is about lightweight hash function. The last one is elliptic curve cryptography, very important. Like if you go for research, you will come across them often. Okay, this one, elliptic curve cryptography, and it works based on public key crypto system or asymmetric key crypto system. Two different keys would be used. So here, like very interesting this one. That is why some mathematics also I have kept here so that you can get some ideas that how it works, but it is difficult. It's not easy. Like we are not so much intelligent just going through it. We can remember, we can understand. Again, you have to go through it to have better understanding. So here, why this particular elliptic curve cryptography is important and also it is considered as lightweight. We have some information here, like traditional one is the RSA. Reverse Samir Adelman, based on them, this name has come. So RSA. To provide same level of security, okay, for a particular encryption and decryption algorithm or cipher system, if we consider. So in case of RSA, you see some information is there. The key size would be 3072. So key size would be very large. But if we use ECC, elliptic curve cryptography, key size would be only 256 bits. It will provide same level of security. That is information, and that claim is also correct. Like it is verified already. Like I have not provided any information here that I have thought of. Okay, I have collected, and these are proven facts. Okay, so you see that is the strength of ECC. Only smaller key size, it can provide same level of security which RSA provide with high level of key size. Okay, now there comes the importance of elliptic curve cryptography. When we talk about elliptic curve cryptography, you see that here this particular equation is very much similar to ellipse, but not exactly ellipse. So that is why the name came. That it has similarity with ellipse. You have like parabola, hyperbola, you have gone through in mathematics. So it is ellipse, looks like ellipse, but not exactly ellipse. So, here the ciphertext, plaintext, and also key would be determined from this particular curve points. So this curve we are considering to generate keys, plaintext, ciphertext, everything based on this curve. Okay. Now here a particular factor is considered, that is P. P stands for prime number. Always it has to be considered like the values that you are considering or the coordinates that you are considering on that particular curve, elliptic curve, okay, they should not go beyond a particular threshold value. To limit that, we have considered a prime number. Means it is considered, okay, not me, okay, except me, the other researchers have considered, okay. So prime number would be there. Like when we talk about advanced encryption standard, not advanced encryption standard, rather RSA, okay, like asymmetric cryptography, they have considered prime numbers because prime numbers has the capability of giving higher security. Okay, here also it is considered, but it has another reason also, like the points that we are considering, it may be key value, it may be plain text or ciphertext. It will not go beyond a certain value. So we are limiting it, that all values will stay within that particular range, would be within that particular range. So that p-value is considered, and this p-value would be the numbers. And here, A, B, these two constant values are there. These constant values also will have a certain value. You cannot choose anything arbitrarily for them. Okay, it should satisfy this kind of equation, like 4a cube plus 27b square would not be equal to 0 if you divide by p. And also while choosing A and B, they will range between 0 and p minus 1. So these are certain conditions should be satisfied while creating different plain text, ciphertext keys, all based on this elliptic curve. Okay, so now we'll look into some other things are there also. We are going out of time. Some operation we'll look into. Okay, so here if we talk about like plain text is there, for example, Q1 is the plain text, Q2, for example, key. If we add these 2 points, okay, if we add them, it will give us ciphertext. And ciphertext would not be the point connecting these 2 points, making a straight line. Rather, it would be the mirror image of that value. So Q3 would be the result, mirror image. It would not be R, because it would not be in the same line, that point, ciphertext. It would be a value in some other part of the curve. Yes, it has a relation. It would be just mirror image, okay, image with respect to this mirror. Okay, it would be a mirror image. And here, when we are talking about finding the values, like this is Q1 having the coordinates or values like x1, y1, it has value like x2, y2. When we are choosing Q3, it has value, for example, coordinate value like x3, y3 when we want to determine. So it will have gradient slope value. So that value would be determined by this equation. If they are defined, Q1 and Q2, they are defined values. They are not the same points. On the time, M would be the gradient value. You know that how to determine that. In straight line, you have gone through same formula. But if they are same point, on the time, gradient would be like based on the tangent value. It would be tangent because 2 points, they overlap each other because we are dealing with the same point, like ciphertext, plain text same. For the time being, we consider that it has some other meaning. We will come very soon. Next slide. So if we have that, if the 2 points are same, on the time straight line would be the tangent to that particular curve. On the time, the M would be that one. You will make derivative, you will find it. You will make the derivative of that curve. Okay, first derivative, you will get it. You know that perhaps. So in this way, we can get the x3, y3 point, that is ciphertext we are talking, and the corresponding M value. M value is there, x1, x2 value is there, M value is there. Once you find x3, you can put here, you can find y3. So this is the mathematical some background, not so much complex. Okay, we have not gone through that. Means I have not gone through. If we have like sometimes we have subtraction, the subtraction can be changed to addition. Okay, how it can be changed? Like here, point subtraction is there. Here it can be converted to this. Only y value would be negated because it is the like all points are just opposite to each other in that mirror. Reflection in that mirror. Okay, so you can consider that in that way. Similarly, then you can add it to get the corresponding ciphertext. So no subtraction. Subtraction you can change it to corresponding addition. Okay, in this way. Then we have doubling. So doubling actually, how it came. So doubling has some other role here. Okay, like what we are telling, like sometimes a value is private. Okay, we are talking about asymmetric cryptography. So we have a value, constant value, that is secret value. that is the private key. If you just simply multiply with that point, okay, it will give you another point, okay, it will give you public key. And that point would be, for example, some base point or something. Okay, we call it base point. And base point, we have the information. It has, like choosing the base point is not easy. It follows also certain condition. Like group number is there. If you multiply the base point with group number, it will give you 0 point. Okay, then that point would be considered as the base point. And from that point, you can generate public key, private key. By just private key would be chosen as integer value. And if you multiply with base point, it will give you corresponding public value, public key. So in this way it works. So then we have some other discussion, okay, and they work based on those primitives, okay, lightweight security primitives. So it is about identity-based encryption. In this particular encryption, what happens? Like simply, these are something different, okay, not exactly those different type of lightweight cipher technique, not them, but these different security primitives also can be, they are lightweight, and they can be applied in IoT devices. How you can get some idea, like in traditional, they work in a different way. Here, they are working in a different way. Okay, how they are working, like identity-based encryption by this name, you can understand that we are using identity of a particular person or identity of a particular device as the key. And that from that identity also, this also belongs to asymmetric key cryptography. When you are using identity of a particular device, for example, ID number, or for example, in case of us, email ID, for example, you are using that as the identity. You are encrypting the message that you are transferring. With that identity, you are making the ciphertext. When the receiver will receive or IoT device will receive, it will just request the private key corresponding to that particular identity. It will get, and that private key, the Bob here or another IoT device, okay, receiving IoT device, will get it requesting public key generator. Okay, we are not private key generator, because we are requesting private key for that particular identity. Once it gets it, so you can understand that here that public key, private key relationship is maintained, and it is easier actually to compute in IoT devices. Why easier? Because here they are using a simple key like identity or something as the key, and they are not, in traditional case, what happens, they are a trusted server, okay, from that trusted server, they request that public key. That public is not available easily, like the way we are telling in data encryption standard or RSA, okay, asymmetric key cryptography. In that way, it does not work. So the key that like any people get, okay, for their data or in that application, it is there, for example. So that public key they get from some trusted third party, that public key, okay, and or certification authority is there. So they get from there, public key infrastructure or certification authority is there. They provide the public key, private key. It's not that I'm generating there. Okay, it's not that. So here, the mechanism is very simple, that they are using ID instead of taking from third party. It would be really time taking. Before actual message communication, there would be handshake. It would be time taking. For these devices, it is not possible. IoT devices, it is not possible. So their time is over. So they are using their some identity, and they are encrypting the message, and there would be, for example, a server or some kind of server would be there. They will provide the private key for that, and they will use that. So in this way, identity-based encryption works, and it is supposed to be lightweight. People are working there in this direction. Similarly, attribute-based encryption is there. In this particular category of encryption mechanism, what happens? They are not going to use any kind of identity or those kind of stuffs. Rather, some kind of attributes will work as the key. Like here, some examples are considered. Some examples are considered like some attributes, like department HR clearance level, for example, 5. So they will use those values attribute values. We are calling it attributes. So they use those attribute values to generate the key. So while generating the key, they use some kind of Boolean algebra. Okay, X or gate or AND gate, that kind of Boolean algebra they use. They make the key, they encrypt the corresponding message. Similarly, at the server side also, if they have those attributes only, they can make the corresponding key. Otherwise, it is not possible. So they have to have the similar attributes or that kind of attributes. If they have the receiving end, they can decrypt. Others, no. So in this way, attribute increase, and you can see that XOR mechanism, all this, or ORing, ANDing, those are very faster. Those are very faster. So you can easily generate the key. So there is lightweight concept is there. Then we have this one, proxy encryption. It is also efficient. Okay, very efficient. Okay, it is going to end. But here, apparently it seems that it is really time taking. Okay, it is computationally intensive. But if we talk about sensor network or some other network, it makes improvement while computing the corresponding ciphertext and decrypting it. It makes improvement. How? For example, here, original message, they have encrypted with some public key. Okay, so ciphertext 1 is given there in the Alice side. And what they are doing, they have the public key of Bob, and Alice has encrypted that its key with Bob's public key. Okay, that kind of stuff is made here. Then the ciphertext as well as that encrypted key both are sent to some other server. We are calling it server. There is a certain reason why this particular mechanism is followed. I'm coming to that. First, you understand that once that server gets that ciphertext as well as re-encrypted key, that re-encrypted key is applied on that received ciphertext, means ciphertext again it is re-encrypted. So another ciphertext it creates and sends to actual receiver, that is Bob. Bob it applies his private key to get back the message. Now, what is the beauty here? Any other server or adversary gets this ciphertext too, they cannot decrypt it because they don't have private key, the corresponding private key. That is the claim, and it is true. But here, how it is efficient, lightweight. You see that here only two users we have considered, Alice and Bob. If we have multiple users, Alice is sending his message and Alice wants to send the same ciphertext to multiple different receivers. So it just encrypts that message once because it wants to send multicast. It is going to happen multicast. So it encrypts the message, creates the ciphertext, sends to this intermediate device, that is server, another server, proxy server, and also it encrypts another key. It sends it. Key size is normally small compared to block size or message size. So yes, it will take some time, but not so much time. Some energy, but not so much energy. Now, this server can do all operation like encryption, any other operation. Encryption would be done, and once it encrypted, it can send to multiple different receiver. But if Alice was to send it, on the time it has to encrypt multiple times. So it's overcoming that problem. So that is why here, like that technique is there to provide security, but here that intermediate device, that a proxy server is playing important role to make it energy efficient. So in this way it works. Then we have homomorphic encryption. Very, very interesting, this one. Like here, just I will give you a glimpse. Here you can see that in this figure, like you have plain text, you have encrypted, you got the ciphertext. On the ciphertext, you are performing some operation like multiplication, addition, or subtraction. On the ciphertext itself, you decrypt it, you get the operation applied on original plain text. So in between, okay, nowhere when you are thinking of applying some operation on it, you are not getting back the plain text, you are not performing some operation, no need to do. So homomorphic encryption, it also makes it little bit less computation, less energy consuming. It's in this way, because it allows to perform any type of operation on the ciphertext only. No need to get back the plain text, then perform operation, then again make ciphertext transmit. No. You can perform operation on the received ciphertext. When actual receiver will receive, that operation is already applied on the original plain text. So that is the beauty of homomorphic encryption. In this way it works and it makes lightweight in that sense. Okay. So that is the end. Okay, that's all I thought of sharing with you. And yes, coordinator has given me the time. Thank you. Okay, to finish it. That is end. Okay, and that's all. I don't have anything else. That's all. So thank you.
Any queries? Offline participants? No. Over to online participants. If you have any queries, please feel free to ask either through chat or you can unmute yourself and ask.
Ma'am, how we can have an access to these recordings?
No question means.
Am I audible?
Yeah. Yes. Hello guys. Do you have any question? Okay, this email ID is there. If anyone has any further query, okay, later on, you can ask me. Okay, guys. Okay.
Okay, thank you, sir.
Thank you. Yeah.
Thank you, sir.
Am I audible?
Well,
Hello?
discussion insightful, was engaging session on lightweight cryptography, and your clear explanations have greatly enriched our understanding on how lightweight cryptography solutions are shaping secure systems, especially in resource constrained systems. We truly appreciate your valuable time and contributions, sir. Thank you. Over to the participants. Now we are breaking for a lunch break, and we'll meet you at 3 p.m. sharp. We'll have a session started at 3 p.m. Now we are breaking for lunch. Okay, thank you.
Am I audible?
Good afternoon, one and all. So we are revamping our first day session afternoon. So now I invite Dr. Vinod P. Sir on the topic security issues in federated learning. Vinod Sir is presently working as professor and head in the department computer applications at CUSAT. Between March 2023 to March 2025, he was a Marie Curie Fellow at the University of Padua. He was also a postdoctoral researcher at the Department of Mathematics, University of Padua, Italy. Additionally, he was a postdoctoral researcher at MNIT Jaipur, Rajasthan, under the ISEA project on mobile security. He holds his PhD in computer engineering from MNIT Jaipur, India. In 2020, he was awarded the Seal of Excellence for a Marie Curie Sklodowsk Curie Individual Fellowship by the European Commission. Subsequently, in 2021, he was awarded the prestigious Marie Curie Fellowship by the European Commission. He has numerous research articles published in peer-reviewed journals and international conferences. He is a reviewer of several security journals such as IEEE Transactions of Information Forensics, IEEE Communication Surveys and Tutorials, and Elsevier Computer Communications. Vinod Sir's area of interest is malware analysis, security of AI, cyber threat intelligence, federated learning, and natural language processing. We welcome you, sir. Over to you.
Thank you. Hope I'm audible. So thanks for the kind introduction, and thanks for hosting me to such a wonderful workshop. So since it's the first day of the workshop, I thought I would be talking on the security of federated learning, uh, in general, giving uh, a basic idea of what are the different types of attacks that are possible in the federated learning domain, and what could be the mitigation strategy. And then I will open up the forum for some latest research work that is going in the domain of federated learning. So to start building the tone of the lecture, the first important thing that we need to understand is like why the data cannot be centralized. What is the reason wherein we don't want our data to be centralized? The first and foremost understanding is like if the entities are sharing data to a common curator or an aggregator, then one interesting point to understand is if the curator or an aggregator loses at some point of time, then the whole data that is transmitted by the clients or the worker node to the curator will be lost. So in the simplistic scenario, we say that basically the curator or an aggregator is the single point of failure. Additionally, we also observe that when we want to do some sort of an analytics and we want to build up certain solution, we need data. And these data is collected from devices. Maybe the devices are having data in non-uniform distributed manner. That is, every device doesn't have the uniform distribution of the data. Also, the data may be sensitive. Like, for example, our research data. So if we plan to build a model by directly sending a raw data to some source, which we call by trusted source, we should also understand that the trusted source, even though they don't see the data, they can be curious or they could be malicious. They could try to infer some information out of the data. So let's try to understand at this point of time, we want to build a machine learning solution or a machine learning application where we don't want the nodes or the clients or the workers to directly share their data, but collaboratively develop a model which they can use later for prediction. So this idea of collaboratively building a machine learning or deep learning model without directly sharing data between the participant, this idea is called as federated learning, and it was coined somewhere in year 2017. So this is a preliminary diagram that you see on the screen, where on the top part you find out a server, which is also called as an aggregator, and in the bottom you see certain devices which are having privacy sensitive data, or maybe the data is very, very important. So the notion over here is that the clients or the nodes or the workers, they are not interested in sharing their data with other participants, or they are also not interested to share the data with the central server, which is also called as curator in some technical literature, but they want to develop a model. So in this case, which is an architecture of centralized federated learning, which is not a strong architecture, but still what happens is in this federated learning process, the master is a server who would try to set up a basic configuration of how the federated learning will take place or how the training process will take place. So the configuration might include the number of rounds or iterations of the training, a basic structure of the model, with the number of layers, the hyperparameters, and then what the server does is the server shares this basic model to each of the client or the workers. So now what the client does is they will take their local data and then they will take the zeroth model that is shared by the server, and then they will build a model which is called as a local model. Now, the point to be understood over here is that now these clients in the next round where they are trying to build an updated model will not share the data with the server. On the contrary, they will share the model parameters with the server. So the server doesn't see the raw data that is held with the client. Rather, what the server observes is the model parameters, which could be, let's say, the gradient, maybe the direction, which could be basically the layer-wise activation, which could be the weights that is received by the server. Now, the job of the server is to take all these model parameter and apply certain algorithm for averaging. So there is one famous algorithm which is called as federated average, which they will try to average all the parameters, and then it will develop a next version of the model. And this version of the model will be sent in the next round to all the clients. And this process is repeated. The clients will take their local data. Again, they will train the model. They will share with the server. The server will aggregate. This keeps on repeating until the number of federation round as proposed by the server and as agreed by the clients terminates. So eventually what happens through this process is that the clients will have a global model that is collaboratively constructed by the participation of all other clients using their local data. And the expectation of the federated learning is that the performance of federated learning model should be at least close to the conventional machine learning or deep learning model, wherein the clients are sending a raw data to a centralized server, which is observing the data and building the model. So on the top, on the right side of the screen, you will see that what is expected is the difference between the performance of a federated learning model that we have created now, a collaborative model, and the conventional model should basically differ by a small quantity called as delta. That means the performance should be equivalent to the baseline model. So if we fundamentally try to reason, what we have done now is that since the data is not moving out of the client system, we can think of in some sort that the sensitive data, since it is not leaving the system, the privacy is somehow maintained. Okay, so the sensitive data is withheld with the client and the server is not observing the sensitive data. So we might expect that there is some sort of privacy preservation. So let's try to understand through certain schemes whether if the data is not still available, can we still breach the privacy? Maybe you can. Okay. Yes. So generally, there are three different variants of federated learning. And today I would talk more about horizontal federated learning because it is the beginning of the lecture. So there are three different classifications of federated learning. One is called as the horizontal federated learning. In horizontal federated learning, what happens is the feature space is basically constant, but the sample space is different. So for example, we can think about there is a bank and multiple people, let's say all of us have an account with some bank called as X. the features related to every entity will be similar. There will be an account name, there will be an account number, and so on. So on this slide, you can see an example where we are talking, which is taken from OpenMind, which shows that there is an online publisher of a blog, and there are certain users. And every users, so if you look here, that there are multiple users, so multiple samples, but every sample is actually referred by or identified by the same features. So the features are identical. For example, the articles that are read, articles that are written, number of people who are following the blog, and so on, and the last attribute being the label. So in an essence, in sample-based federated learning, the data set, they will share the same feature space, but the samples will be roughly different. On the contrary, there is another concept called as vertical federated learning. In vertical federated learning, the feature space will be different. For an example, let's say that I have an account with the bank, so I have certain attributes of me maintained by the bank database. But at the same time, if I visit some mall and I do some merchandise, the server over there would maintain a different feature space for me, right? So maybe the analytics can be done like based, if there is a collaboration between the bank and a mall, some sort of an analytics can be done, or some applications can be driven wherein they could try to see my expenditure and try to, let's say, propose me a sort of a loan. Okay, so in vertical federated learning, what happens is the sample spaces are identical, but the features will be distinct. For an example, if we try to enhance the example that we took previously, like a person who is participating in writing a blog or reviewing a blog, okay, maybe also a person who has got a great interest in reading, he or she visits a bookstore. So if you can see that person C, who is active blogger, is also a great reader. So so the information that is maintained for person C, which is shown in green color, is like title, category, and author. Okay, so this is called as vertical federated learning. And then the third form is called as the federated transfer learning, where we have the same idea of transfer learning approach. So let's try to reason more about the security and the vulnerability part. So why federated learning can be thought of vulnerable? So as we said, the whole concept of federated learning is there are multiple client nodes which are also called as workers, and they are held responsible for the training process. So which essentially means that in the federated learning process, there is no control on which client is joining the network and which client is leaving the network. So somebody can be active in the network. Somebody can be simply dormant. Okay, they may be simply observing the traffic. So this is the first problem. The second problem is, since there are many entities available in the federated learning process, how do we determine which client is legitimate or which cluster of clients are legitimate and who all are malicious? Okay. And the third important thing that we have to understand is, like, since there are multiple nodes, every nodes have different resources in terms of hardware, but also they have different volume of the data that is available. So the data space is also different. So which is called as non-independent identical distribution. So the data is not similar. The data, on the contrary, with every node is different. So our assumption it's a myth rather, that every device would be having an equal amount of data, and that is how we get a model which has better performance. But there are definitely clients which are low quality, which are generating a low quality model because they starve for data. The data that they are having is not sufficient. So what is security by design? What is primarily security by design today? So the fundamental thing that we have to understand is that whenever a machine learning model is constructed, we always have a myth that this model will be deployed into a domain where legitimate users will be there. Okay, so the idea of adversary is not even considered while constructing the model. First. Second thing is, we assume as a model developer that the training data and the test data, they share identical distribution. There is less elasticity in the test data, or the evolution of the test data is basically happening in a horizontal manner. It's not escalating. For example, when you talk about the domain of let's say malware evolution or the attack, you have like malware which is appearing in wild, like in fractions of second. And another myth is that the source of the data that we are taking, it does not depend upon the classifier. So we can never make a claim that always for image support vector machine will be good, or for an image convolution neural network would be good. And finally, the data source that we grab has got some amount of random noise. So with this principle, what we have today is a type of security system which is basically reactive. So there is an arms race between the attacker and the defender. And we expect that the attackers, they try to be dynamic and they create more attack tactics in order to be ahead of defender. So in the reactive system, what happens is that the adversary will try to analyze the system. And then what happens is the adversary finds out the weaknesses of the system and devise an attack. Now, once an attack happens, the defender waits and look at different artifacts that map to attack, okay, and evaluate which attack has to be responded immediately and develops a countermeasure. So one fundamental thing all of us have to understand at this point of time is the reactive systems are basically working like a signature-based system. Something that we know the pattern about, we can detect it. On the contrary, if there is something that is appearing as novel attack, the reactive systems will be failure. So what is the solution that is proposed by most of the security groups is to develop a proactive system. So in a proactive system, what is intended while building a secure system or a solution is that the defender or a solution provider should be actually inside the shoes of an attacker or an adversary, which means that the defender should be should be able to simulate or mimic what an adversary does. So what defender does is, like, defenders would try to model an adversary. So when we say model an adversary, the defender should know what are the different adversarial tactics. So they should be very smart enough. And if we want to understand what are the different adversarial tactics available, then we have to refer to some sources like Mitre repositories, where we have classification of different attacker tactics, different attacker techniques, and what are the procedures they follow to craft an attack. So let's build a proactive system where the attacker simulates the attack. So once the adversary simulates an attack on an infrastructure, they would try to evaluate the impact of the attack that has been translated onto the infrastructure. So then what they do is like they will basically rank all the risk, and then they will try to prepare a mitigation plan in order to deceive the highly risky event. So if we are building a proactive solution, definitely an organization who is trying to prepare a security defense solution can understand the ongoing attack, and also they can prepare for the future menace. So in the nutshell, what I would like to conclude by this slide is that most of the security system that we try to develop should be proactive in nature. So having said this, we cannot ignore the presence of adversary. How strong solution we develop, we should try to understand that there will be definitely an adversary who is trying to exfiltrate vital information out of our system or network. So an adversary basically makes use of different types of knowledge about a system. Okay, so the basic threat model that we have is called as a white box attack. So when we translate this threat model to the machine learning or deep learning domain, in the white box attack, the attacker, who is supposed to be an insider, okay, which is the strongest class of an attack, he or she is aware about the training data set. He or she is aware about the representation of the information, how mathematically they are represented, and they know the internals of the model. So when I say the internals of the model, they know the number of the layers, the complete architecture, the hyperparameters, and so on. Somehow, when we are creating a security system through machine learning solutions, we can actually use, or we can implement a white box system, a white box threat model, in order to evaluate the robustness of our model. So we can actually mimic an insider attacker in order to find out how robust our AI system is. On the other side, we have a gray box attack model where the adversary is having a limited knowledge about a system. So when we say limited knowledge about the system, the adversary doesn't know what type of data has been curated in order to develop the deep learning or machine learning models. But he or she is aware about the feature representation. They know the internals of the model. Finally, the strongest threat model is called as a black box model. And as the name is evident in the black box model, threat model, the adversary doesn't have the knowledge about the training data set. He or she is unaware about the feature representation, and they are also unaware about the internals of the model. But still the attack is possible. So that means there is a model which is available on cloud. The possibility that is available to the adversary is to present the data to the machine learning model and see the response. And just by looking at the response, the adversary can craft some type of attack. On the right side of my screen, you see a type of a chart where you can see that there are three color cubes, black, gray, and white. And as we move towards the horizontal axis, towards the extreme right from one end to the other end, what we observe is the knowledge the attacker is having in the black box scenario is very less and towards the end, they have more knowledge about the system. So to attack a white box, a model is relatively easy. So let's talk about, since I've built the basic tone of the lecture, let's talk about the different types of attacks that can be crafted into this federated learning model. So I have a long deck of slides, but maybe as soon as the time overs, I will stop. So I'll try to give you the maximum that I prepared for this lecture. So the first type of an attack that is inherited in the federated learning domain is from the seminal paper that was published in 2019 from a group of researchers from Massachusetts, which is called as Deep Leakage from Gradients. A wonderful paper to read, and I think somebody who is practicing security of AI, they should definitely read this paper, which is called as a deep leakage. The title of the paper is Deep Leakage from Gradient, and it has, I think, more than 5,000 citation, and it has become the basic science now in security of AI. So this idea is basically inherited in to create attacks or to evaluate attacks in federated learning. So to sum up what we have seen in collaborative learning, there are multiple nodes or participants or workers. Their main objective is to build a collaborative model, okay, without sharing the data. And what they share essentially is the parameter. So what somebody observes in the network is the parameter or the gradient. So the common assumption that we said a few minutes back is like, since I'm not sharing my data is not leaving my machine, I'm just sharing some numbers to the central aggregator. So I feel I'm secure, but can we leak some information by observing gradient is what we are going to investigate. So the goal is to investigate the leakage of private training data that all of us are having just by looking at the gradient. So how this is possible? So I'll just skip this slide because it is more or less on federated learning. So what is happening? Let us revisit what is happening in case of a federated learning is every node is using a basic model that is shared by the server, and they are using their local data to prepare a local model. So basically what is happening is that each node, let us say I, or each client, let us say I, they use a model that they have received in the previous round, referred in this diagram, in this equation as W subscript of T, and they try to calculate the gradient. So they calculate the loss, and the job is basically to minimize the loss with respect to the parameter. So we essentially try to calculate the gradient, which is shown by this equation. So this is done by one client, and if there are n clients, all of the n clients will be doing the same work. And now what they will do is they will share all these gradients to the server, and the server will apply certain algorithm and aggregate all these gradients, which is shown by this equation by lambda wt is 1 by n, summation of j is equals to 1, and it is the gradients from the individual client. So in the next round, the server sends this aggregated information to the client. And when the client receives this information, they start building their model. So before that, what happens is the server will try to update its parameter. So when it has to update its parameter, what it will do is it will use the old value of the gradient, okay, old weight, sorry, and it will try to subtract with the loss, which is like learning rate and whatever it has computed, and this will be given back to all the clients. Now, the problem exists over here. The basic problem is the availability of the aggregated gradients that is available to the server. Now, we can assume that the server is basically honest, but the server is curious. Okay? Server doesn't see any data, but it is curious. The goal is, can the server use this information to find out what is the data available with one of the client? Okay, so it wants to create the private data of the client. So how it will look at? So let us try to see this diagram, which is having two sections. So if you look at the normal participant, okay, where we see the picture of a cat, the picture of a cat is given to the model. Okay, the model performs a prediction. Okay, and you have an actual label. Basically, you try to apply some sort of loss. Okay, simple, we can say actual minus the prediction. If there is a high difference between the actual label and the predicted label, what happens is like we backpropagate the information. Okay, so we try to find out the derivative of the loss with respect to the model parameter. Now here the attacker plays a game. Now what the attacker does is, attacker does not know what is the data that is held by the client. The attacker will create a random input with an associated random label. Okay, so the attacker does not know anything. The only information the attacker is aware about is the gradients from the client. So now what the attacker does is, the attacker will use his created random image. It will supply this image to the model that it is having, because all clients are sharing the model and it is developing a shared model. Now the attacker will try to predict the class label corresponding to the random input. It will compute the loss. Okay. Then if the loss is not similar, again, it will try to minimize this loss. So that is what it is trying to do. So what we need to understand at this point of time is, the attacker is having the information about the shared model, and it has its own version of the model. It will try to find out the difference between both the gradients. And what mathematically we can imagine in a layman's language, like if two vectors are there, the first vector is for the original model and the second is of the attacker. If they are both orthogonal to each other, that means they are dissimilar. On the contrary, if the attacker is able to somehow craft an input such that the output of its model is closer to the shared gradient, what will happen is, he is somehow able to generate the input that was used to train the original model. So what essentially is happening here is, what attacker does is, attacker tries to minimize these two gradients. Okay. And when it tries to do this, it is trying to also change the input, which is shown over here, partial derivative of the difference with respect to the input and its class label. It will keep on doing this until and unless it will try to generate the original input, which is the input of the cat. So let's try to understand how this happens. So what the server, which is now an attacker, what it tries to do is, it will try to start with a random input and its associated random class label. It doesn't know anything. And now what the attacker does is, for its dummy data, it will compute a dummy gradient. Okay. And the dummy gradient can be computed using the same formula that we are having, where F is a model, X is an input, W is the parameter of the model, Y is the class label that attacker has assumed, and it will try to generate the dummy gradient. Now, he has the knowledge of the previous gradient. He has computed its own gradient. If both these two vectors are aligned together, it's a knowledge, it's a guess to the attacker that the dummy input are same as the private input that the client is using. So what the attacker will try to do is it will solve this optimization such that it will try to find out X and Y, keeps on changing X and Y, such that the difference between the dummy gradient and the real gradient is minimized. So what we are trying to do over here is it will try to find out a minimum X and Y, minimum change in X and Y, such that the difference between delta W prime and the real gradient is minimized. And so if you copy this value over here, this equation translates to this. So this is one of the attacks that were performed, and this is one of the paper that I'm talking about, which is called as deep leakage by gradients in machine learning. Now, how we can infer the data that is residing in multiple clients in the federated learning situation? So can we use a gradient leakage attack for federated learning systems? So what is the goal? The goal over here for an attacker could be a client or it could be a server, is basically to recover the private data that is held by the client, okay? Because the communication that is happening between the client and the central server are basically the parameters. But the fundamental problem is like, for example, if you look at the federated average algorithms, gradients are never shared. It's basically the model weights that are shared. So can we craft an attack if we know the information about the model weights at different time steps in the federated learning scenario? So the key difference of the attack that happens over here is the attacker need not know the knowledge of the gradients, rather, or any hyperparameters like the learning rate or so and so on. Rather, the only information the attacker requires is what type of loss function every client is using, and what is the weights they are sending to the weights of the model they are sending to the server. Okay, so two fundamental piece of information is required in order to craft this attack. One is the weights these clients are sharing with the server, and secondly, the loss they are using. And this loss is basically configured by the coordinator, who is the server, when they are setting up the federated learning process. But what an adversary does not want to know is basically the training data the client is using. So how this attack is crafted by an attacker? Attacker could be either a specific client which wants to infer data about other client in the federated learning scenario, or the attacker could be the server itself. Okay, so the whole job of an adversary is to basically use a dummy data, a random data, and a random class label, and apply certain sort of a gradient leakage attack to find out the private data that is held by the client. So that is what the attacker will do. Now, how it will do? So the focus is to basically attack the standard algorithm of federated learning, which is used for aggregation, which is called as the federated average. There are many algorithms in federated learning for aggregation, but let's say the standard one is like there is you receive data from multiple clients, you just average it. So the focus is attacking the federated average algorithm by recovering private data using the model update. At any iteration, like any round t plus 1, let's say step is 2, every client will try to update their weight using this equation, okay, which is a classical equation in machine learning for during backpropagation, which is like the new weight is equals to old weight minus the learning rate multiplied by the loss. Okay. So if we have an input X, like a picture of a cat, and its class label is like a cat itself, then the loss function can be actually substituted over here, saying like the new model weight at time t plus 1 is wt plus 1 is equals to the old weight minus the learning rate and the derivative of the loss function with respect to weight, and you have an input x star and y star is the label. So, which means that if we try to substitute this value of loss over here, the above equation can be transformed in the form of a loss function. Now, this is the basic thing that happens while training, but how we can use it for attack. For an attack, the attacker requires 2 snapshots of the model in federated learning. One is the global model, which is available to any participant in the federated learning architecture. And the second one is the current model weights of the client, which has to be victimized or which has to be targeted. So in order to create an attack, in the attack process, at any time step, 2 important information is required. One is the global model weights, which is represented as W superscript G of T, and the updated local weights of any client K which has to be compromised, which is WK of T plus 1. And we know how it can be created. Now, since it's a gradient leakage attack, the attacker will try to first construct a random input, which is denoted by X hat, and its random label, which is called as Y hat. And with this random input and the global model that is available, the attacker can compute the gradient. Okay, so the gradient can be computed. Just we have to take this input, pass it to the model, you get the output, which is shown over here, which is a dummy gradient. Now, what the attacker tries to do is, his job is basically trying to bring this dummy gradient that is computed as close as the approximate gradient. So what is an approximate gradient? We have the model parameters of the server. There is in a new round the parameters of the client. If the direction of these 2 vectors are similar, what the attacker would like to essentially do is somehow try to bring this dummy gradient as close as this, because this is the global model and this is the client model. And if this part becomes close to 0, essentially it means that attacker is able to develop an input which is more or less similar to that of the client. And here K is a client that I want to attack. I repeat, the job of an attacker is to somehow create a direction of a vector, okay, which should be close to the approximate gradient. And approximate gradient can be computed because every node in the federated learning scenario has an idea of the global model. And if we know the global model, we can definitely try to create a new model update at a new time step. Okay, so if we try to find out the difference and the dummy gradient, if they are all closer, we can say that the input can be created. And this is called as the deep leakage in federated learning. So this is an optimization, and F stands for Frobenius norm. This computes the magnitude. So let's try to assume somehow that this loss is computed. When this loss is computed, next what the attacker has to do is to change the input, okay, so that this could be minimized. This becomes 0. So what the attacker will try to do, it will take its old input, which may be an image, okay, and it will update it, generate a new image. The class label is generated, and he also has assumed a learning rate, which is also generated. Now there is a big problem with this type of an attack. This attack can be crafted if the attacker is resourceful, okay? Because if you imagine, the adversary has to actually do 3 things. He has to find out an X, he has to find out a new Y, also he has to find out a learning rate, which is represented by gamma. Also, we know in the machine learning domain that everything is random. The weights are random. Now we are adding one more complexity, that instead of guessing X and Y, it also has to guess what the gamma. So how do we actually create an optimization? How do we means how an attacker will create an optimization so the complexity in order to craft an input is minimized. So let's try to understand how this can be done. Before moving to the next part of this slide, let's try to summarize what we have learned in terms of what is deep leakage by gradient that we have seen in the previous slide, and what is deep leakage by gradient in federated learning. So we divided this table in different parameter. One is the aspect or the attributes that are considered. The second one is the algorithm, the attack algorithm or approach that we are using, which is DLG. And the third one is essentially the deep leakage by gradient for federated learning. So the first row, it says that if we look at the deep leakage by gradient algorithm, the whole idea is based on sharing the gradient, which is a strong assumption, which federated average algorithm doesn't support. But in case of deep leakage by gradient for federated learning, instead of gradients, the whole idea is thought of by sharing the model. So which means that the gradient access in deep leakage by gradient attack is mandatory, but on the federated learning attack is not required. What type of information is available to the attacker in case of deep leakage by gradient is the gradient, the loss, the learning rate, and the optimizer. But in case of the federated learning attack, it just has to know the model weights and the loss function. But on the contrary, in deep leakage by gradient, the attacker somehow has to optimize deriving new X, Y. But in case of federated learning attack, the complexity is more because it has to derive X, Y, and the learning rate. 3 things are required. So this is done by matching the true and dummy gradient. On the contrary, here we have matching the dummy gradients with the weights. That is why you have an equation where you have the dummy gradient and approximate gradient. This is less practical because gradients are not shared. These are more practical. Weights are shared. The complexity is less over here because I just have to find X and Y, known the gradient. But here it is higher because I have to find X, Y, and delta. So let's try to get away with this gamma. How do we get away with this? A one-on-one on a very fundamental concept called as Frobenius norm, which means that given a matrix to us, The Frobenius norm is basically the sum of squares of square root of the element, and essentially it gives you the magnitude. So if you have a matrix which is converted into a linear vector in the machine learning or deep learning domain, we say if we flatten the matrix, what we try to do is we take every element, we square it, we sum it, we take the square root, which is essentially equals to the magnitude. So this Frobenius norm, if you would have seen in my previous slide, was actually used to find out the difference between the dummy gradient vector as well as the approximate. Okay, so how we can get away with gamma? So sorry, little bit of maths, but I think it is it's important to understand if we have to understand the attack. The problem is like we have to get away with this alpha learning rate. What we need to do is we take this alpha, just rearrange this equation. We have alpha, which is represented by the difference in the global weight minus the updated weight at the client, and then you try to divide it with the gradient. So if I take, so basically these two weight matrix, if I try to take the Frobenius norm, essentially I'm trying to compute the magnitude. So if I take the magnitude of the numerator and denominator, I can have a new equation of alpha, which is represented by the magnitude of the difference in the global weight minus the updated weight of the client divided by the magnitude of the gradient vector. And if I take this alpha and substitute it over here and I rearrange this equation, it becomes one of the beautiful mathematical formulation where you have a vector divided by magnitude is nothing but a unit vector, which basically gives you the direction. I repeat, a vector divided by the unit by the magnitude is nothing but the unit vector. And when you have two unit vectors and you are comparing both these two unit vectors, if both of them are similar, then we have come to a place where the data that we have got is similar. So basically what we are trying to do is like we take this alpha, substitute over here, we rearrange it. So this is basically a unit vector. So essentially what we have done now, the previous equation where you have basically gamma is away from this, and you are trying to essentially compare the two unit vectors. And if the unit vectors align in the same direction, it means that the attacker is having a notion of guessing the input. So with this, what we try to do now, what the attacker will try to do is it will take the old X, it will try to do some changes, and it will try to create a new X and Y. And with this, the attacker can guess the private data that is available with the client. So what is the summary of the gradient leakage attack? And it's a strongest attack, and it is breaching the privacy of sensitive data. We will talk about how to mitigate this. So what we learned previously, to summarize, if both vectors point to the same direction, similarity is higher, okay? Cosine similarity is higher, basically the loss equals to 0. If both vectors are orthogonal, okay, so which means misalignment is basically higher and they are dissimilar. So the adversary will try to solve the previous optimization until and unless the dummy inputs and dummy label, okay, creates a direction which is similar to the direction of the client update. Okay, so this is why it is better, because we are only concentrating over here on the direction. We have got rid about the learning rate, which is alpha. Now comes a very interesting domain, which people have. I don't know in India, whether they have started speaking, but in Europe, this is like something that is now a big debate. It's an eye opener, but in India, it will be something we will be speaking about, which is called as machine unlearning. Okay, so let us try to discuss what is machine. Sir, you can stop me anytime when we have to stop. Okay, so we will talk about what is machine unlearning. You see this world map with flags over every country. Every country is actually talking about sensitive data and how this sensitive data should be handled. So, what does a general privacy regulation speak about? Any privacy regulation would be speaking about users' data. Okay, I just try to sum up few of them. We will not discuss all, but the one that is on the last part is something that I will be discussing. The first one is right to access, which means that as an individual like Vinod, okay, I request my personal data to be accessed by a specific authority. And in fact, at any point of time, I can ask who is using my data. The second one is right to data portability. Without my permission, the data that somebody has collected cannot be ported to some other organization. I have to give the right for that, which is called as data portability. This is right to be informed. I think most of us have gone through it. Like when we try to fill the form somewhere, you would have seen your data would be collected. Are you okay with this? You just say tick and then you submit it. And the most important thing that I would talk about today is Article 17 of GDPR, because I was doing my research last 2 years in Europe. And Article 17 of GDPR, which says, or the General Data Protection Right, clearly mentioned that any user at any point of time can ask a business organization to delete its private data. So if I have given my data to a company like Uber or Ola, and tomorrow I say you should delete my data, they have to certify, they have to show me the data is removed. Okay, they should not say your data is no longer available. Not that, they have to give me an evidence which I can understand as a layman, like my data is nowhere available with them. So machine unlearning is a paradigm which people are now practicing because there is privacy laws like in European GDPR or the California Consumer Protection Act, where the user data should be transparent. They should know how the data is flowing, where it is flowing, how it is being handled, how it is ported. So there is complete transparency that is needed. So what is machine unlearning? So in machine learning, basically, you just see this part, don't see two cylinders over here. You start with a large amount of data and then you create a model. But at some point of time, if I feel that my data is sensitive, which is shown by this gray color cylinder, I would request to the data or the model provider that you have to delete my data. So this original model should scrub away the memory of my data and create an unlearned model. So this is called as unlearned model. And this unlearned model will not have any information of my sensitive data. Its performance will be, in a layman's language, equivalent to an original machine learning model, which is retrained from scratch without the presence of sensitive data. I repeat, how this unlearned model should behave. The unlearned model should behave in performance similar to a model that is retrained from scratch without the presence of my data. So you have two models: an unlearned model, a model that is retrained, a model that is retrained from scratch. If the performance of the output of these two models are similar, then you will say that unlearning is effective. This is one of the indicators to evaluate unlearning. So having said this, in another couple of minutes, we would be talking about what are the general classification of machine unlearning techniques. So essentially, there are two basic classification. One is called as an exact unlearning. So many algorithms falls under exact unlearning. In the exact unlearning, the sensitive data is physically removed from the data store and a machine learning model is developed. On the contrary, in approximate unlearning, what is done is that we try to change the model parameter, okay, and then try to check the output of the model to evaluate the influence of the sensitive data point. So we try to scrub the model parameter such that if I present the sensitive data, the prediction will be close to 0. So we keep on changing the parameters of the model. So there are two types of algorithms. So sorry. So the first, I will just take one example of each. So the first one is called as the exact machine unlearning algorithm, which was proposed by the group of Papernaut. I hope all of us knows who is Papernaut. If not, we should know. And it's a very important group in the domain of machine learning, and all of us should be reading because their papers are only available in ICLR or NeurIPS or IEEE SNP, so which is supposed to be the top conference in the computer security domain. So the first work of machine unlearning was published in 2015, and then this work of 2021 done by the group of Nicholas Papernaut gained lots of attention, which is based on exact unlearning. They do unlearning in 4 steps. So their technique is called as CISA, which is the first S stands for sharding. The second S stands for isolation. Third step S stands for slicing. The fourth alphabet A stands for aggregation. So what CISA means, in the sharding process, take the large volume of data that we have and we divide the data into multiple subsets. And each subsets are technically called as the shard. And then using each of these shard or the subset, different models are created. So let's say I have 5 subsets. I will try to build 5 different models or submodel which are trained using the shard or subset. So when we do a training, when we write a deep learning algorithm, we have seen that the complete data is divided into some sort of batches. We do a forward pass, then we calculate the loss, error, we backpropagate the error. So here what they did is the shard is further divided into smaller batches, which is called as slices. And each submodels are iteratively trained on these slices until the model performance converges. Eventually, the output of all the submodels are aggregated, maybe using different aggregation techniques like majority voting or simple averaging to have the final prediction about the data. So what is the beauty about this? So I just show quickly diagrammatically. We start with the complete data set. We divide the data set into number of subsets, which are called as shards. Take the shard, use it to create a classifier, and then we aggregate. The advantage of this unlearning technique is that, let us say, if the user sensitive data is available in shard number 1, you just have to remove his data from a specific slice and retrain this submodel. Submodel 2, submodel 3, and submodel n need not be changed. Okay. But on the other way, if you talk about retraining, what you do is you physically remove the data and you train the model from the scratch. But in this case, only a specific submodel is trained. Why this is so advantageous? Imagine that I'm building a large language, I'm developing a large language model for my organization, okay, which is curated from numerous amount of data. But then there is a student who is saying that, oh, there is a private data about me, which is collected. So if I have to actually remove his data and start building the model from scratch, it is not a sustainable solution. It cannot last, right? So what is the advantage of CISA is like we just have to retrain a specific part of a submodel, any submodel. The only point is that all these submodels have to be procured by the model owner, because they should know which shard is having a sensitive data, go to a specific model, then retraining. So that is the only limitation. So what is the advantage of CISA? It reduces computational cost because you don't do training from scratch. You just point out a model, you try to train that model, okay? And it maintains the prediction accuracy because there are different models which are not retrained. So you perform an aggregation, but also it's an advantage because if my solution is improving, I can create a new shard, a new model, and then aggregate it. So it's relatively scalable. But what could be the limitation of CISA? The limitation is that if you look in the basic development of a deep learning model, the model tries to learn interactions with different data points. So the data points are never isolated. So the patterns are learned by the interactions of different data point. But in CISA, what is happening is each models are essentially trained using different shards, and these shards are non-overlapping. So which means that the models, they don't see what other model is learning. So basically they don't learn complex patterns as our neural network does. So this is a basic problem with this technique. And definitely the storage, because as I said, we should have a copy of multiple submodels in order to remove the information about the data. So now I will do a quick one-on-one on an approximate unlearning technique. This appeared in a very famous A-star conference, which is AAAI. And this approach is called as amnesic unlearning. Amnesic is basically a state or a health condition of a person where he or she has a capability of forgetting things. So they forget things fast. So amnesic unlearning, this biological phenomenon was translated to the machine unlearning domain. This is basically a rapid unlearning technique wherein if a requester has got specific instances to be removed, it will be removed fast. I repeat, if somebody is collecting my photograph, and there is a face detection system collecting my photograph, and I don't like that it has collected few instances of my photograph. Maybe I'm dressed very casually. I don't want it to be collected. So if I want those instances to be removed, okay, instance-based unlearning, then amnesic unlearning is effective. But since it's approximate unlearning, it does not physically remove the data point. It does some changes on the model parameter. So let's try to understand how it will try to do the unlearning approach. In amnesic unlearning, there is a concept called as sensitive batches. So we have our data. Data is divided into batches when we try to do the training phase. So the definition of a sensitive batch is a batch that contains the sensitive data. If any batch, let's say a batch B1 has 100 instances, and in that 100 instance, the first instance is my photograph, then I will say that complete batch is sensitive batch. So amnesic unlearning essentially keeps track of the sensitive batches, and sensitive batch by definition is a batch consisting of sensitive data. So let's try to understand what is the basic training process. We start with a model architecture, and we start with some random parameters, random weights. We say we fix the number of epochs, which is E. We fix the number of batches. And then while training, there will be multiple rounds of parameter update. So that means for every iteration, I take the batch of data, I forward pass my data, compute the loss, backpropagate the loss. I do it for the number of iteration. And finally, the model theta m is created, which starts from the initial model parameters, which is theta initial, plus for every iteration and for every batch, we try to add the update to the initial parameter. So we have now theta model, the original model, which having the information about the sensitive data. So in case of unlearning, as I said, it tries to maintain shall I continue? Yeah. So it tries to maintain a collection of sensitive batch, which is shown in this slide by the word SB. And I reiterate again the definition of a sensitive batch. Let us say now a user says that you have to delete my sensitive data. So the amnesic unlearning will try to find out the batch numbers where the sensitive data is spread across, and then try to basically subtract the sensitive batches from the previous model that we have created. So this is our previous model, which is theta m. You try to subtract the sensitive batches. So this approach will essentially work well, because if you look at this particular equation, if the number of sensitive batches, suppose let's say we have 100 batch, if 90 batches are sensitive, so you are aggressively changing the parameters of your model, which will bring down the utility of the model, the performance of the model. On the contrary, as I said, this will be effective if the amount of sensitive batches are low. If you have low number of sensitive batches, so total 100 batches are there, and let's say there are 2 or 3 batches where sensitive data is present. So basically, you try to perform the subtraction operation 3 times. So this is not an aggressive update. On the contrary, if the number of sensitive batches are huge, and if we want to have the same utility or the performance of the model as the original model, what we have to do is we have to perform some extra time steps of fine tuning. So you have to fine tune your model with the remaining data set so that the performance, the old performance of the model should be retained. So I would talk about one last algorithm on approximate unlearning, which comes from the concept of knowledge distillation. So in knowledge distillation, essentially, what we are trying to do is we are trying to create a small model which is called as a student model. Okay, there is a teacher and a student. A teacher model is knowledgeable. It is a huge model. It memorizes everything. From that teacher model, we are trying to inherit essential information into a small model, which is called as a student model. How this is done? This is a very famous approach in deep learning. How this is done basically? So you take the input, you pass it to a complex model, a teacher model, which contains thousands of layers. And you take the same input, you pass it to a student model, which contains hundreds of layers as per my definition. And you try to find out the output from both these models. The output over here is basically a softmax probability. And then you try to compare, during the training, you compare whether the softmax obtained from the teacher and the student are similar, okay, which are also called as soft label, and you compute a loss. So this is called as a distillation loss. At the same time of training, you are actually computing another loss at the student. So here you have the soft label. So we have a soft prediction. Then for every input, you have an original label. So you will find out the maximum from the soft label. You get a single value, which is its prediction. You have the original label. You compare these two. This is called as a student loss. And sometimes this is also called as an hard loss. So basically, in knowledge distillation, what we are trying to do is we are trying to compute a loss which is solving two loss functions together. One is called as a distillation loss between a student label and a teacher label, and a student loss which is between the hard labels of hard label and the hard prediction. So I'll quickly run over this slide in the interest of the time, and I will leave it for you to further read it. So the advantage of knowledge distillation is like we use knowledge distillation in order to develop a model which we want to deploy on a small handheld devices because it's a compressed model. But this model will have the same knowledge about the teacher. So it is computationally very efficient. It uses less memory power and it would be faster. It's scalable because the model is smaller. You can deploy it into multiple instances of the device, and it gives better generalization because what we have done is, since we have smoothened the decision boundaries by inheriting the knowledge from the teacher, it tries to guess the future instances properly. So another 2-3 minutes for the loss function, and then we will see how it is done for unlearning, and then how we will attack unlearning. So as I said, in knowledge distillation, you solve two loss functions together. The first one is the student loss, which is basically our traditional cross entropy loss, which we try to find out by the student's model and the ground truth. So you have a softmax output from the student model. You take the maximum value, you get the class label, and then you already have the ground truth corresponding to the input. You try to find out the cross entropy loss, which and then you have another thing called as a distillation loss, which you compute between the output of a student model and output of a teacher model. And to convert this soft labels into probability, we divide it by a large value, which is sometimes called as temperature T, which will convert it into a uniform probability. So essentially, what we do at the student end is we calculate a total loss, which is equals to the cross entropy loss or the student loss, plus it is equals to the knowledge distillation loss. And the cross entropy loss equation is written like this. I don't discuss all these things. So how this is used for unlearning? So again, this is a very prominent work in the domain of knowledge distillation and machine unlearning from the group of NTU, which was also published in AAAI. Their group is very active in unlearning. So what they did is like they created a student model which did not had any knowledge about a sensitive data using two different classes of teacher. One teacher is supposed to be highly knowledgeable, and another teacher is called as an incompetent or a dumb teacher, whose job is to make the student forget. So there are three types of model. One is a competent teacher, one is a dumb teacher, and a student model. So essentially, what happens, I will show through the diagram, is like the student basically tries to get the useful information from the competent teacher. So that means the output that is obtained from the competent teacher and the student model should be minimized. So when we have to compute two probability distribution and we want to find out whether these two distributions are alike, basically you try to solve KL divergence. So essentially we want to minimize the distance between the competent teacher and the student on the preservation data set, the data that we want to preserve, but at the same time, we want to actually distill wrong information from the incompetent teacher to the student. So we want to minimize the KL loss between the student and the incompetent teacher. And we try to solve this optimization. Through this, what will happen is the student will actually have the relevant information of the preservation set, but at the same time, it will forget the information about the sensitive data. So let's try to, I will come to this slide later. Yes, let's try to ask one important question now, like if I try to have a setup where federated learning follows, and we would like to essentially, any client would like to request for a deletion of the of sensitive data. Is it possible for an attacker who could be a client or who could be a server to leak what sensitive data is forgotten? I repeat, the research question now is, a client wants his data to be deleted, which is deleted. Can an attacker try to regenerate the data which has been deleted, okay, in the federated learning setup? So that is the question that we are going to ask, and we are going to do an attack on the federated learning system. So if you look at the real world scenario, the scenario could be there are multiple users, and these multiple users, which are called as the data owners, have given their data to a trusted machine learning developers or providers who are building the machine learning models in their behalf. And once these models are constructed, then there is a machine learning as service provider which tries to aggregate this model and deploy. And people like us can actually use this application or can query the model using an external prediction API. So the question that we are asking now is, if the sensitive data is removed either using an exact unlearning approach that we studied like CISA, or an inexact unlearning algorithm like amnesic unlearning or knowledge distillation, can the attacker somehow again create the data that is deleted? If he can create, then what is the need of basically machine unlearning? Privacy is already breached. So let's try to understand. The goal of an attacker here is two. One, to create the original data, which is called as inferring features, or even if he cannot infer the feature, can he guess the class, whether Vinod's data is there or not? Okay, so the goal of the attack is feature inference or unlearned data. So who are the participants in this model who can behave as an attacker? We know that in the federated learning situation, we have a server and multiple client, and the server in the machine learning as a service paradigm basically sees two instances of a model. One, an original model, which is having the memory of the sensitive data, and also it has a snapshot of a model where sensitive data is not present. So two instances are there. So if you have an original model and if you have an unlearned model, if you subtract both of them, it means that you can infer basically the data that is deleted. For example, if you have a set consisting of 5 numbers, 1, 2, 3, 4, 5, and you want to remove 1, the output is 2, 3, 4. So if you have 2 instances, if you subtract, you should be able to generate unlearned data. So that is the first thing. The second one is like, there are many clients who may behave as an attacker. They don't have access to the internals of machine learning model. So they can simply push the data and then see the response. Can they, just by seeing the response, can they try to find out whether the data was deleted from the model? It is rather intuitive in machine learning domain. If you have a model and if that model remembers your data, if you give the data to the model, the prediction score or the confidence that you get from the model is relatively higher. On the contrary, if you have a model which doesn't have your data as a member, you give it as an input, the confidence score will be lower. So when you observe from the output of a model that the prediction score is relatively very less, the attacker can have a clue that the instance has been deleted. So that is what is done in the second type of an attack. So let's try to look at this. So maybe I discourage you to read what is written, but you can see the diagram. So there are 3 entities. You have a model developer, which uses large collection of data, and it trains a machine learning model M. And this machine learning model M is uploaded to in the server. And we as a user can actually query the machine learning model to get a response. Now let us see how the attacks can be crafted. Let us say some user has asked for removing one picture of a cat. So when it is removed, you apply some unlearning algorithm, which could be either exact or inexact, and you develop an unlearned model MU. Now, the machine learning as a server has got 2 instances of the model, the original model M and the unlearned model MU. If it can subtract these 2 information, it will try to generate the instances of the cat. because it knows model internals. On the contrary, the user who doesn't know the model internal will basically actually query the unlearned model, compute the prediction. Okay, if the prediction score is relatively lesser, it understands that that particular data instances have been removed. So this is the whole idea of inversion attack. So I'll just spare a few minutes more and then maybe we will close. And how it is, how you can do an attack. The attack is rather similar to what we learned previously. Like if you have a sample X, its associated class label Y, which belongs to data set, what you can try to do is like during model training, you repeatedly execute the model update equation where the model update at k+1 instance is the old model update subtracted by learning rate and gradient. And if the server who is an attacker is having an excess of original model theta and an unlearned model theta u, if it can subtract, it will try to generate a gradient corresponding to the forget set. How the attack is created? The server who is an attacker, we will assume, will start with the same old concept of generating a random input X and its associated class label Y. After doing this, since the server is having the access of the global model, the server will try to compute the gradient corresponding to X and Y, so which is represented by this symbol, lambda prime. And finally, if the server is having an access of an unlearned model and the original model, it can compute the cosine similarity. If the cosine similarity is higher, it means that it is able to generate a direction which is similar. So it will keep on changing this X and Y until and unless the gradient that it computes on the dummy input is similar to the target. So over here, target is represented by delta star, but this formula is nothing but it is the formula of cosine similarity. If both vectors are aligned, until both vectors are aligned, the server keeps on changing the input. So which means that the objective of the server now is to find out an input X such that the cosine similarity between the gradients of the unlearned model and the original model should be similar. So, so basically it will try to compute a minimum X by simply changing the input until this loss is minimum. So in this way, it will try to find out the input. So, so this is what it does. And the last one is like label inference. So as I said, in label inference, the attacker does not have access to the internals of the model. It can only query. So if it can query, it can look at the prediction from the unlearned model and the original model. And if the difference is higher for a particular class, it will understand that particular instance is not remembered. So what is the intuition of server? The attacker. The attacker in the first step will create some samples which are called as probing samples. So for every class of the instance, let us say if we have an MNIST data where 10 classes are there, for every class, the attacker will try to create certain probing sample. Okay, and these probing samples are created with the original model, and it will use this probing sample to probe the unlearned model to see the output. So how it is done is like, first, it will create a data set consisting of n probing sample. For every sample, when it is given to a model, it will get a prediction which is called as Y. And if you have C classes, you get values for every class. Next, It will solve this optimization. It looks to be very crazy, but it is very easy to understand. What it will do is it will take its dummy data and it will give it as an input to the original model. So it will get a logit. So before the softmax. And if this softmax is not equals to the target label, what it will try to do, it will change this X. So it will apply a minimum change in X such that the class label that the attacker wishes inclines with the class label of the original class. So this optimization is solved. So first you maximize this and then you minimize every X. So essentially what you're doing is you're bringing your direction of the class towards the target class. So once this is done, it will try to take X, it will give it to the unlearned model to compute the prediction. And once this is done, it will do it for all probing sample. It will try to compute the average. And finally, what will happen is that it will try to find out the maximum class label from the previous vector, and the maximal class label is basically corresponding to the unlearned class. Because the whole idea is when you have a model and when you subtract information from the model, you get an unlearned model. If you basically subtract both of the instances, you actually get the gradient corresponding to the forget set. So this is basically the attack that can be crafted. And how to get away with this? What is the solution? The solution can be basically, I will not discuss in depth because I leave it for the subsequent speakers. I saw there are some speakers who are speaking on this. The one of the solution is that when the clients are sharing the gradients to the server, the clients should basically add some minor perturbation to the gradients. So they can add some Gaussian or Laplacian noise to basically the gradients. And then in that way, the gradient leakage attack is difficult. First one. Second one, we can apply some sort of pruning techniques. So pruning in terms of gradients, some gradients which are not important, they can be pruned, they can be made zero. So that way also it can be mitigated, or you can use some cryptographic techniques, one of them which was discussed today, like homomorphic encryption or differential privacy or secure multi-party computation in order to basically mitigate this. And just before I leave, I would like to just discuss one last slide. Yeah. Which is one of the strongest attack which is under picture, which is called as a membership inference attack. So in the membership inference attack, the job of the adversary is to somehow guess whether a data point was used for training or not. So imagine a hospital is having the medical record of a patient, and let us say an attacker is an insurance company. If they are able to guess, we know this visiting an hospital and he is suffering from a sort of a disease, maybe they can charge me more. So that is called as a membership inference attack. So in membership inference attack, you have an original model trained with huge collection of data. So you have a model now. The adversary basically tries to give an input to the model. And if it is able to find out the label, then it understands that that particular data point is used for training. So maybe it's like I was prepared for 2 hours lecture, but since we squeezed some time, so I can leave this slide, and it is self-explanatory. And if you have any further queries, you can write to me, and also I'm ready to address the query. And before summing up, like I largely work now in cyber threat intelligence, or security of AI, malware analysis, basically, which was my PhD thesis also. So, if you have some common interest, maybe we can work out together, we can explore together. So, because I take every opportunity of my lecture also as a forum where I can learn and I can move ahead. So thanks for the opportunity, and I hope I could have given 5% of something that you can absorb. So thank you.
Thank you, sir. Offline participants, if you have any doubts, you can clear it now. Yes, sir. So one.
Yeah.
Yeah, it was a really nice session, sir. I had a couple of doubts, one in unlearning and one with KD. So, like with unlearning, right? We were
One unlearning other?
like distillation.
Okay.
Okay. So in unlearning, we were working on some problem like the system is heterogeneous IoT systems, and we were figuring out a personalized IDS, intrusion detection system. So the thing what we observed is like, given that the global model, the initial global model already has a priori knowledge of the data distribution. So in the heterogeneous network, what we are observing is
no. This is a strong assumption. It should not be. It always the model is non-IID. So the global model should not have any knowledge about the distribution of data. It's a strong assumption, actually. It should not have.
Yeah. So the thing is like we wanted to make it personalized. So we tried with unlearning, but we were getting better results when we were actually using transfer learning and some kind of like fine tuning approaches, say LoRa or something. So why would it be like that? Maybe because of this assumption.
Yeah, that is what I'm saying. It's a strong assumption that the data is IID. It's a strong assumption. It should be
not that assumption. I was telling like the data is, or the pattern, general pattern of the cumulative data set is already known to the model.
No, it should not be. It
should not be.
No, it should not be known. And if we have to, but there is a problem, actually. I'll tell you. There is something called as security, and there is another coordinate of a security which is called as performance. So we can scrub this knowledge away by introducing some sort of a noise to the input distribution space. But the problem there is like the performance that we achieve in that case will not be effective. But I think we should not solve a problem in which the curator knows anything about the data. It should not know any. Or maybe there is a solution which I am solving with my PhD student. I will tell you. Maybe she came here for space also. Like for her PhD, I was solving something called as poisoning attack. Okay, which is like a fundamental attack, and it is something that can be easily crafted by an adversary. So we relaxed the assumption that the data is not data distribution type is known to the server, and the class is also known to the server. Okay. But that is a strong assumption. In that case, the server can create an auxiliary data. Okay. But how you can approach this problem in a proper way? You should start with a simple assumption that the server doesn't know anything. But we can have an assumption that there is something called as warm-up learning, where initial rounds we can have some trusted clients. And with this trusted clients, you build a model. And then let's say first 20 rounds, and after 20 rounds, you infuse the attacker. The basic assumption is in first 20 rounds only our model would have converged. Okay, but this warm-up learning is also debated by many many people, like how do we do it? But instead, I would like to point out to the last part of my lecture where I said that you can always start with a random guess of data, probe the model, collect the label, and try to build a proper input. So, for example, in this previous case, you have two instances of model. So you gave an input to the model, you got an output. Then you gave an input to the unlearned model, you got an output. You try to find out until and unless the difference between both of them will be like larger. Okay, because an unlearned model should not remember your data. But how do you create this data is like you try to find out the output distribution of a given input from the model. You have a target class label. At every point, you find out a label for which this distance is larger. You perturb your input. So when you perturb your input, again, you give it to the model. This distance will become smaller. You will reach a point, you get an input which is closer to the output distribution. So in that case, you are not even guessing the data, you are creating data by yourself. I think that is the solution that we can do.
And with the KD, actually, like assuming that my FL is having a multimodal setup, and I'm using KD for like infusing data to the global model.
Okay.
And in round 2, how do I revert it back?
Why do we? I don't get why do we ever use knowledge distillation in federated learning situation? I'm not.
No,
I'm
like,
not understanding
yeah,
the use
okay.
case.
Mine is like a multi-model setup, and one model is, let's say, maybe a machine learning model,
Yeah.
a basic tree or something. So technically, I'm not able to aggregate it directly with other deep learning models, right? With the clients.
Yeah.
Yeah, like assume 5 clients are there, and 4 are having deep learning, and 1 is having an ML model. So I am expected to use some kind of KD to at least map the weights as such to make it unique, not unique, identical, or at least similar.
Okay. But in this scenario, like I would not suggest knowledge distillation. I would suggest to find out latent representation of every model and concatenate it. Or I will suggest you something which is basically called as split learning. So basically you have the server which is having the head of the model, and then you have multiple clients which are having multiple type of model. The tail can be different, and then you can give it to the head, and the head will try to find out a representation. And then you backpropagate the loss from the head to the individual model. I think that could be the easiest solution.
Yeah. Actually, split we had tried out, but
I'm working on split learning
again, it's
attack.
creating some problems.
We are extensively working on attacks on membership inference attacks on split learning. So maybe like if you want, we have a very good group who is very active in split learning. So if you want, we can actually discuss more about it.
Sure, sir. Thank you.
Yeah. Yeah. So as a defense part. Yeah. So the first, so the problem is like we want this inference to be more challenging. So if we look at the federated learning setup, client will give something to the server. So we add noise before transporting. So for it could be differential privacy. Differential privacy is one of the solution. You can start with basically a Gaussian noise or a Laplacian noise. It could be differential privacy. It could be, in fact, secure multi-party computation plus differential privacy, which is called as that technique is called as I'm not getting like yeah. I have an answer to this. I have a recent paper in uh, uh, which is the title of my paper is called as SEC-CTIS, which is published in FGSS, Future Generation Computing System. In that, what we SEC-TIS, SEC, it is a CTI paper. Yeah. So what we are doing in this paper to answer to your question is like we have a collection of client and some of the clients in this collection of clients are called as validators. Okay. Now, what is the job of the validator and how blockchain can be used? You have a blockchain where there is a model, initial model. When you do a federated learning, this initial model will be copied to all the clients. Okay. And the job of the client is to use their data and generate a local model. Now, this local model will not be aggregated. Instead, this local model will be given to the validators initially, and these validators will take their local data and try to find out prediction for each of the local model. So it will get the prediction for each local model. Now, what we do is like from these local model, we will try to rank the clients for which the prediction probabilities are higher. So we have a subset of client, aggregates their parameter and put it into the blockchain, which will be the next round model. But there is a question. The question is like, how do you trust this validator? So what we did in this our research is we said like if you have to trust a validator, we used a concept called a zero knowledge proof. So what we did is the validator will do two things. The validator has to basically publish the hash of its private data and the hash of the model output it has computed to the blockchain. Okay, and everybody will be having a verifier contract. They will contact the IPFS, then download the model, and then they will see whether the validators are. They are not computationally efficient. But one thing is like if yeah, I'll tell you. But the solution can be applied in different domain. Federated learning is applied in two applications. One is called as cross silo, where number infrastructures are limited, data is higher. Second is cross device, where in many nodes are there, data is less. So I fear ZKML. We use ZKML library will not be faring well for cross-device federated learning. It has to do, it will work on cross-silo, but I don't have an answer for actually cross-device. Yes. So in this paper, we have done two things. We are calculating the reputation of the client, dynamic reputation. Maybe I will leave my slide. Last week I was speaking in Forensic Science University about this. So the reputation of the client is calculated, and then we can create an incentive. That is an easy approach we can do.
The defensive mechanism could be
Yeah.
How validate that it is secure?
Yeah.
Is there any mathematical model?
A good question. like I did not explore, but there is a recent NDSS Usenix paper, proof of certifiability in learning, which is a recent paper. But I am solving a problem with my student. I will tell you what is the problem statement that we are solving in the domain of machine unlearning. Is like, you say that your data is deleted. How do you certify to the user whether the data is deleted? So we are using a blockchain concept, because every data that is deleted, some instances will be available in the blockchain record. So there are only 3 archive papers, and so there is no published papers. But there is a algorithmic proof of certifiability in machine learning, which is a recent paper. I think if you give me 1 second time, it should be there in my system also. Yes, this one. This is a Usenix paper. Is there any more questions? Thank you, ma'am.
So over to the online participants. We have around 40 plus online participants. If there is any question, please, you can either unmute yourself or come up with a chat.
Or,
Thank you. Okay, sir. So yeah.
or maybe if you want, you can also write to me at this address if there is something that you feel. Okay.
Thank you. Thank you, sir. Sincere thanks for today's enlightening session on security issues in federated learning. Your deep dive into the vulnerabilities and defense strategies has provided us with crucial perspectives on safeguarding privacy in distributed learning systems. We are grateful for your time, effort, and the knowledge you have shared with us. Thank you for being part of us. Thank you all.